on because I'm actually monitoring it just behind me. I've got a slightly different setup today, so now the chat monitor is right behind me and I can see it pretty well, but I'm still waiting to see this thing go live. It says preview. Okay, here's starting live. Let's see, and I should be live. It says 15 seconds live. Let's hope that it should come on any second, guys. Good, I'm seeing it start. Excellent, and I hope I see audio. I think the audio is coming in. Is it coming in okay? Does everybody have audio on 2 channels, not just 1 channel? I'm seeing issues potentially with audio on 1 channel. Hold on, let me check. Are we having issues with audio? No, I think we're okay. Okay, good. All right. Hi, everyone. I'm going to slide down the chat in just a second, but I saw a couple questions that were asked right up front, and I'll just mention something about that. There are a couple people who are asking me about Solar Parker probe and whether or not that's a really good mission right now. It's an excellent mission. We're learning amazing things that we didn't have a clue about before. Some things had been postulated before, and we've been arguing about them for literally decades, and especially the heating question about why the corona is so much hotter. And it looks like alphane waves may be in the lead. There's been a lot of debate as to how generated waves from some of the kinetic processes and magnetic processes that are happening in the solar atmosphere, how those might actually be the source of some of this heating. And right now, it looks like alphane waves are taking are the winning horse, but it's still very early in the game. And I haven't yet read the papers. I'm going to be going to AGU here in a very short while, literally next week, to give a talk, and I'm going to go see if I can go find Noir and chat with him a little bit about some of this, and see some of the other talks that are going to be on this subject. So I will definitely come back with more answers than I have now. But that's a really cool mission, and it's very exciting right now because there's a lot of new things that were unexpected. And then also, some of the main questions I've seen thus far are, is Solar Cycle 25 coming? Yes, it's coming. Anybody who's watched the videos recently, you're hearing me talk about Solar Cycle 25 more because we're seeing more sunspots from Cycle 25. We're seeing a lot more high latitude spots, especially in the southern hemisphere, which is the one that's coming first. And then in the northern hemisphere, we're beginning to see high latitude spots in the northern hemisphere as well. I think, as a matter of fact, there's one on the solar disk right now. It's not a sunspot, but it's a bright region. And so this is going to continue to accelerate over the next few months. Maybe around spring is when we're thinking the terminator will finally come, but we will see a continual ramp up of activity as expected right before the terminator hits, which is when really Solar Cycle 25 starts. And then activity will light off like a crazy, bucket. It's going to cause a lot of solar flares will start popping and all that kind of stuff. But we kind of just have to wait for this ramp up period, which could be a few months yet before we start really seeing the activity. But those of you who are amateur radio operators should see your solar flux slowly rising. We're back in the marginal range as it is right now, back in the low 70s for solar flux, and that helps radio propagation increase. So, things are looking good. So just hang in there a little bit longer. So those are a lot of the questions that I got right off the top. Let me check the chat real fast to see if everybody can hear me. Give me a thumbs up if everybody hears me and I sound good and everything looks okay, and we'll get started, all right? So just go out. You can probably still hear me. You just can't see me now because I'm off camera scrolling down the chat to see how things are going. Okay, good. I see thumbs up. Wonderful. I feel a part of Parker Solar Probe. They let people get their names put on it. Yes. Excellent. So good. Make sure you get your names on the Mars landers too. They're doing a lot with a lot of the Mars missions as well. You can get your names on those as well as they land on Mars. Okay. Oh, thank you for getting my ham license. Yes. WX6SWW. And let's see. Lowest KP recorded. Any comment? Sure. Hi, Jerry. Oh, good. Okay. So let's see. It looks like everybody's good. Okay. Fantastic. I'm looking good for sure. That's wonderful. Okay. Audio's working. For those of you who have my phone number, those VIPs in my Patreon committee, you guys have my phone. You can get a hold of me. If my mic goes out, please call or text anything to get my attention so we don't have that ridiculous thing that happened 2 or 3 courses ago that I'm still not living down. I still have it up on YouTube. So if you ever want to see 17 minutes of me talking to nobody because there was no audio and I didn't know, go have a laugh. It's a couple courses ago. So anyway, so get a hold of me on my phone. I have it right there. So if it rings, you know, you have to deal with it. It's my safety measure because this is a one-woman show. Okay, great. Thanks so much for all the good wishes. I see a lot of people I was hoping to see here. Hi, Francina. Hi, Jerry. I love that you guys are tuning in and learning so much about space weather. There are a couple people who ask questions about radio noise and about some of I think one of the questions in particular was how do we know what frequency is going to come out? How do we know that higher frequencies come, you know, closer to the solar atmosphere than lower frequencies? If you want that information, go see the first 3 classes on solar flares and radio bursts. I did 3 prior classes on this particular topic because it's so comprehensive. Really, solar flares and radio bursts are some of the most intensely important space weather phenomena as far as it is contributing to effects at Earth. For, you know, the huge set of stakeholders who are amateur radio operators and emergency responders that I talk about all the time, this stuff is critical. Being able to know this stuff in gory detail is extremely critical for you all. And because it, you know, in some cases it can mean life or limb, right? If you have a hurricane hitting and there's no one to, you know, and the amateur radio doesn't work, you know, because there's a solar storm or a solar flare with a radio burst going on, that can make a huge difference in terms of whether or not somebody gets the critical aid they need. So I went into this stuff in very serious detail in essentially 3 classes, and then this is the final one, just to be able to give you that information. So I think it's the second course, it may even be the first course that I go into why you have higher frequency radio noise closer to the solar atmosphere, really near the solar surface, and why that frequency drops as you move further out into the solar atmosphere and then out into interplanetary space. It has to do with the density of the plasma, the density of essentially the charged gas that we deal with, that is the solar wind, the solar atmosphere, and the solar wind. But I'm not going to go into that today, so please take a look at the other courses that I've done. Okay, hi from Argentina. So, oh, thank you so much. Okay, hi Michael, good, glad to see you're here. For you and Jerry, these are a couple of my VIPs in Patreon. You know what, I did not get a chance to check on the 1941 issue, but I think it's a fantastic issue. These 2 gentlemen raised a really interesting point as to whether or not there might have been either a solar radio burst going on or a solar storm happening back at Pearl Harbor Day, right? I mean, look where we are, look what day it is, right? And so, you know, everybody's thinking about Pearl Harbor, and there was a lot of questions back then as to why couldn't they communicate? Why couldn't they communicate over HF radio? Why couldn't they get the warning to Pearl Harbor? You know, there's a lot of theories as to, well, maybe they didn't want it to be there, or why wasn't the phone installed? And one of the biggest questions, of course, is, well, why wasn't there any signals over HF radio? Apparently people tried with HF radio, but it failed. No one picked up on the other end. Could it have been space weather related? Well, nobody would think to check the weather back then for that kind of thing. So, you know what, that's a really, really good question, and I need to go back and check. And it'll be easy to find if it was an extreme event, if there was either a solar flare or a solar storm during Pearl Harbor. Those are easy. But if it was a low-level flare or if it was a low-level solar storm hitting, those are a bit harder. I'll actually have to go back most likely into historical records of the KP index in order to find that. And those are archived, and you have to kind of dig and make requests and all that kind of stuff. So we'll see if I can find it. That's pretty far back. But I do think we had, I do know we had indices. We had the AA index back then. I think we had KP running at that time. They were the Bartels, you know, the different types of diagrams. But we do have historical records of that stuff, so I can find it. So stay tuned, guys, because that's a really, really good question. And wouldn't it be fascinating if that were the case? Because that would be yet another example that I would need to add possibly to this actual class right here. Because that's exactly what we're talking about. We're talking about solar screams at Earth and beyond. This is how solar radio bursts actually affect communications, and not just wartime communications, but disaster and survival communications. all around the planet. And also in space now, because remember, as we bring more satellites up into space, these radio bursts are going to strongly affect whether or not you can hear these satellite transmissions. I mean, that's what happens with GPS. And last time I went into that, I went into a very specific example about the GPS, and I'll review it a little bit here. So, first thing I want to do, though, is thank, let me see which way I stand. I'm going to stand over here. I want to thank my VIP steering committee. These are people who have helped me steer the ship from the get-go, and they join me every month, once a month. We get on a nice long call, usually several hours long, and sometimes several times a month if some of them can't make it. And we talk about where the space weather endeavor is going, how I'm doing at Millersville, what I should be, because I'm going to be teaching these courses at Millersville University starting in January. I'm actually going to give a couple guest lectures in December, in a few weeks. And then I'm starting the official courses in January. So these are the kind of the baseline point of departure for those courses, where I'm teaching TV meteorologists how to do space weather broadcasting. So good luck. Let's hope within the next 5 years you're going to see real credible space weather forecasts on your TV nightly news, when it's relevant. And I have these guys to thank for it. So thank you, you VIPs. And then, of course, also all of the mini course patrons. I couldn't have been able to spend the time to make these mini courses if it weren't for you all. You've chosen the subject matter. You've chosen the angle from which I'm doing this. And as a matter of fact, one course that I really am super excited to get to, which I haven't done yet, is the history of space weather. But that's part of what I'm going to be teaching at Millersville too. So pretty soon, you mini course patrons are going to enjoy being able to see the history of space weather and also how it's been affected by things like astrosociology. So stay tuned for that. But today it's all about solar screams, meaning radio bursts, solar flares at Earth and beyond. And we're going to round out the discussion. As a matter of fact, I'll move over here. We're going to round out the discussion. Let's see if I can stand. We'll see which side I can stand on. No, let's try this side. We'll round out the discussion of solar flares with talking about planetary radio emissions, and then of course implications and lingering questions. So we have covered everything in black. We've covered flare dynamics, effects of radio emission at Earth. Last time I even went through the 2006 December large-scale GPS disruption and the 2017 September radio burst during Hurricane Irma and just shortly after Hurricane Harvey. And I'll review a little bit of those today, not too much, but what I needed to do is still go over a couple of the Carrington-class solar flares. And when I do that, you're going to see why I then include the solar flare myth and its relationship to CMEs. You'll see how we start having problems with the whole solar flare CME relationship once I get to these Carrington-class events. And we'll talk a little bit about hydro flares and also stealthy CMEs, only in the relationship to how it is affected and how it kind of obliterates this solar flare myth, which I'll go into in some detail. You get to see some of the skeletons in the closet of scientists and how, to be honest, it's not just Hollywood that got science or that got space weather wrong. Us scientists got space weather wrong too, and we proliferated a huge misconception of what solar storms really are and what it really is about the space weather phenomena that affect Earth. You'll see all that. That will unfold, and you'll see how nasty it can get, even in the scientific community, when people argue. And then at the end, I'll go through the planetary radio emissions. We'll talk about basically where does Earth fit in. I won't go into it in much detail, but you'll realize that despite all the radio noise that we create with all our satellites, surrounding Earth and actually becoming rings anymore around Earth, we are still radio quiet, relatively speaking, compared to other systems just in our own solar system. So I don't think we have to worry about being too radio loud, because I know there are a lot of people that have talked about that, about how noisy Earth must be. But we're actually pretty quiet, and I'll put that into context for you. And then at the very end, any type of implications and lingering questions you might have, will make it a kind of a free-for-all, because this is rounding out our final discussion on solar flares and radio bursts. So I want to make sure you guys all get the understanding that you need, and if I need to refer you to other classes that I did earlier, then I can. Okay? So hopefully, I was just looking to see if anybody had any issues or something like that. Yeah, Pearl Harbor happened during a solar minimum, just did the math. Okay, good. That's good. I have to take a look. However, remember, at solar minimum, that's when some of the largest events can occur, when we get down to solar minimum, or at least on the declining phase of the solar cycle. So just because we go to solar minimum doesn't mean everything's quiet. We only get right, there's only a short period of time where we get very, very quiet. And, and we're going through that period now. So we'll have to, again, we'll have to see. It isn't just a one-to-one correlation. So let me review just a tiny bit. Let's see, am I on the right side? Okay, good. Everyone who's seen the classes already should recognize this. I'm going to go through these next maybe 10 charts pretty fast, because these are charts that everybody's seen, but I'm just once again setting the stage. Remember that what we're talking about when we talk about radio bursts, for the most part, and solar flares, we're talking about things that come from sunspots. Now, sunspots are dark when you look at them in white light, but they are radio loud. So you can see them in essentially white light here in this one, this picture I'm pointing at right now. You can even see the chart where from the TEM irradiance monitor and the solar flux, where it kind of goes down and then comes back up. That is the darkness of a sunspot as it traces across the sky. But just because it's dark in this frequency, in a visible light frequency, doesn't mean it's dark when you get up to higher, when you get up or when you go to radio wavelengths. So this is I think this is a 1.4 gigahertz image, not 14. My fault. There's decibel missing in this caption. I have to correct that. But you can see these sunspots. Look at them. Look how loud they are. Look how bright they are. So that is how bright sunspots actually are when it comes to radio frequencies. And then when we actually look even further into radio frequencies, we see that the radio frequency itself, the radio burst, doesn't actually come from the sunspot itself. But as you look at this picture, this last picture over here is a picture of the solar limb. So we're looking at the edge of the sun, and that dark region, if I'm pointing to it properly, that dark region there on the limb, yeah, that is the sunspot. We're kind of looking at it edge on. But you see that contour in white? That's above, that's in the solar atmosphere. That is where the radio sound is coming, or the radio noise is coming from. And that is because the magnetic field is popping out of that sunspot, and actually the loop of that magnetic field is over the sunspot. So it's out in the solar atmosphere, and it's really the magnetic field that causes the radio noise from all the processes that are occurring there. And if I switch to the standard model, I trip over stuff over here. If I switch to the standard model, you can see, if I can't, gotta get out of the way though. Yeah, there we go. There's that loop, see it in red down here? If I point to it properly, over here maybe? Sorry. Yeah, if I point to it there's the loop, and it's over the sunspot, over the foot point regions. And when you have a solar flare or even a coronal mass ejection, you have the top part lifts off, and that flies off that way. That becomes the solar storm, the coronal mass ejection. This part here shoots back down, and on both ends, as you have plasma shooting both down and up, you get radio noise. Now the higher density stuff is here, so it gives you a higher frequency of radio emission. You can get hard X-rays, soft X-rays, you can get gigahertz emission easily, microwave emission, all from this stuff here. And then the stuff that's shooting out here, this is where you get the type 2, type 3 bursts, and from the shock wave that pushes this out, or that this thing is driving out into space. And again, all of this stuff is from my earlier courses. So you can actually see the progression of frequencies going down as you move out. So if you want a review of that, please go to my earlier courses. This also, I go into detail about this part, this second part of the model. The yellow is now what was the red foot point. Well, no. The yellow is now what this high part was here, the high part of this loop. Come on, come down. This high part of this loop here. This part here is now what's in yellow on this diagram here, okay? This is the part that launches. This is the CME that launches. So solar flares and CMEs are related. They're not causal. You don't have to have a CME launched from a solar flare, during a solar flare, but you also don't have to have a solar flare when you have a coronal mass ejection being launched. And that's part of the solar flare myth we'll get into. But if you want a review of all of this stuff, that you can get a review of that both in the solar flare in radio burst courses that I did, and you can also get a review of that model in my CME courses. So I think I did 3 of those. So my gosh, you've got, geez, have we done that many? There's like 5 maybe courses where this diagram or that diagram shows up, or I at least discuss it. So depending upon what aspect of the space weather phenomena you want to focus on, that will determine, where in that model I'm putting all my emphasis. But you can definitely get as much information as you need out of that diagram by going back to my other courses. Now here, this was just to remind you that solar flare emission definitely does depend on wavelength. So here we've got the radio emission that's in the gigahertz range on this left-hand side. Here is this is H alpha, so it's not white light, but it's close. And the 2 emissions are being plotted down here in the bottom. And you can see the radio emission peaks first. That's the yellow. If I go down here in this plot down here, the yellow trace, it's over time as the flare goes, and you can see, boom, right there's a peak in radio emission. But then the H alpha ribbons, that's the green line. See how long it burns? It burns much longer afterwards. So really, what a solar flare looks like really depends upon the frequency of light you're deciding to choose to look at the flare from. And so you have all sorts of different phenomena that are occurring and all sorts of different conclusions you can make depending upon what frequency of light you're looking at. And this goes all the way from basically X-rays clear down to UV and white light when we have white light flares. And all of the behavior is different because they all point to a different process at a different altitude that's occurring in the solar atmosphere during one of these events. So again, you want to learn more about that, please go see my other courses. Here's a nice kind of summary chart that goes into this is the last bit of the phenomenology before we start talking about effects at Earth. This is kind of like an overview. On the left-hand side, you can see the overview. This is the sun down here, and then the loops and the flare, and then the CME that is lifting off into space. And you can see with the frequency range kind of roughly labeled as things go outward. And I think I'm stepping on the vocabulary here, the different types of bursts and where they are. But again, this is a plot that I have talked about many times in different courses. And then on this side over here, you're seeing kind of a time plot from the actual flare. You can see the frequency going up on the vertical axis, and you can see the short-term bursts. Here's a microwave burst. You see it here at the very front end of during the flare. That happens near the solar atmosphere, and then you can see the other radiation that comes out. All of these solar screams are occurring as the coronal mass ejection, the actual solar storm, travels in space and travels to Earth. You can get type 2, type 3, type 4 storm, all driven by the big shock front as it gets closer and closer to Earth, and it continues to go down in frequency. And then once it actually goes, and I don't think I have that plot here, but as it goes inside the Earth's magnetic shield, there's even more noise going on. So you can get AKR and all sorts of different types of stuff, and we'll talk a little bit about that when I at the very end of this course when we go into planetary emission. But again, for a review of all that stuff, check out my other courses, okay? So this is just trying to set the stage for you to remember where we were about a month ago when we did this last. Now, flares, when we talk about Earth effects, flares can cause sudden atmospheric changes at Earth. You can see an example of this, and this is one of the things that caused, or that was an effect during the 2006 event, and I'll mention it a little bit, where we had a global scale GPS disruption. Luckily, GPS wasn't really used by many people other than the military at the time because we didn't have these yet. GPS was not something that an everyday person had. So nobody really in the public had a clue that that there was this huge disruption. But the FAA knew, that's for sure, because they were already using GPS to try to help land planes with the precision, with a WAS precision GPS solution that they would use in the, in their airstrips. But this is one of the things that causes problems for us during solar flares. You can get a huge increase in the neutral particle density at low latitudes. And this was an example during, what was it, October 28th, 2003? Yeah, this was, so one of our big Halloween, well, actually, no, yeah, Halloween events. This was one of the big Halloween events, if you guys are familiar with those. I think during one of the Halloween events, was it one of the, I think it was one of the shuttles had like 300 resets or something. I'm not sure if it was one of the shuttles or if it was one of the ComSats, but the Halloween events were there were some major issues with satellites at that time, because the flare, the radio bursts, and then the solar storm that hit afterwards was just insane. Along with the solar energetic particle events, we had just a massive amount of stuff happening during this period. But the X-ray flux, as you can see, is overlaid on this plot. Let me stand back a little bit so you can see it. The X-ray flux was overlaid on this plot here, and you can see right when the flare hit, then the neutral density really changed. They're called sudden ionospheric disturbances, and these lead to big issues with GPS, with any signals going through the ionosphere. So the upper atmosphere, satellite signals will get bent, they get distorted, they get scattered, and as you can see, the effect can last for hours. So these can cause radio communications blackouts, they can cause GPS blackouts, all sorts of things. And of course, they're going to be enhanced near dawn and dusk, because we already have, that's a big transition region anyway. The neutral density of the atmosphere is changing when there's no sunlight hitting it anymore. So that causes changes, and then so effects like this are going to be enhanced even more strongly at dawn and dusk. Which is why in my video forecast you always hear me say, if there's something going on already in the, like a solar storm or something, I always tell GPS users, be careful near dawn and dusk, because that's really when things get exacerbated. And these are reasons why. Okay. Now you probably don't need this, but I thought I'd just put it on here for grins. This is radio frequency spectrum ranges, and so if you need this as a reference, I'll step out of the image for just a second. So if you're watching this course at a later date and you need a reference to where things are, and you want to see potentially where, not just the names of the frequencies and what ranges they're in, but also on this other side, if I flip over here, on this side, you can actually see the types of things that are affected, right? So you have maritime mobile, you have radio, AM radio, then you're getting up to cell phones and 5G, even 5G and satellite communications. I mean, you have all of the standard communications, but even stuff that you may not have figured out when they talk about 5G, for example, or you deal with GPS frequencies, right? You're all dealing with stuff that's in that range. So these are the types of things. All of this stuff can get affected. And here's an example of how that is possible. Let me see if am I on the right side? Here's an example from the 2006 event. This is the Owens Valley Solar Array. This is looking at basically a very high frequency range during an event in 2006. This, as you can see, this is 1 gigahertz up to 5 gigahertz. And everything you see in red is being affected. There's a radio burst going on. These are gigahertz frequencies, right? These are high frequencies. And you can see the stuff that goes in white is covering, over here, is covering between 1 and 2 gigahertz. Now, that's exactly where GPS is. GPS is, as a matter of fact, I think I have it on the, yeah, I do. I have it the L band, L1 band, and L2 band at 1.5 and 1.2, give or take, gigahertz, which is literally right in the middle of where this white band, this white stuff is, right? So for this period of time, which was a good 15 minutes, we had, during this particular event, and this is what I went over in my last course, we had a huge GPS disruption, and it ended up being a global GPS disruption. So anything that on the day side, I shouldn't say global because it's day side, anything that can see the sun, if you can see the sun, then you can hear it scream. And so anything on the day side got affected. And it lasted for a very long time. And here's just one other plot, I think this is the only other plot I've got for this particular event. Again, if you want a more detailed analysis or review of this, go see my prior course, because I went into this particular event in detail last time. So this was the December 6th solar radio burst. That's what SRB means in the title. And this is if you can look at just in the United States and Canada, you can see all of the GPS receivers. And these are receivers that were tracking less than 4 satellites. And I believe, yeah, that was what's in red. And that means they don't have a position solution. You need to have at least 4 satellites in order to get an unambiguous solution for GPS. So basically, all across the northern hemisphere, you didn't have anything. And that was basically the entire day side. And then we also had a loss of vertical guided approach in the precision GPS for planes. So everywhere in the pink area, the very sharp pink areas where it was completely lost, they had to just shut down any airline approach. And then, of course, all in the red and the blue, it was actually affected as well. It just wasn't affected quite so badly. But we had, this is back in 2006, and it was pretty bad. But we actually had a one that's more recent than that. It didn't happen in the United States, but it happened in Sweden. Does anybody remember back in, I think it was 2015, like November of 2015, we had a solar storm going on, and we had a bad actor on the sun, a big sunspot, that fired off several flares, and that was one of the reasons why we were having a solar storm, is because it fired off a solar storm along with a solar flare. And then it fired another solar flare near the end of it. And this solar flare had such a big radio burst in it at the right frequency that the entire airport in Copenhagen had to be shut down. The radio burst was very high frequency, just like this one, and they lost precision GPS for like 3 hours. And it affected all of Europe. I mean, you couldn't get any flights in or out of Copenhagen because they had to absolutely shut it down. So it was a bunch of effects. It was the solar storm effects, plus because they were far enough north, in north latitude, that they were dealing already with issues that was causing scintillation and issues with their GPS. Then they had this solar radio burst on top of that, which exacerbated everything. They finally just called it quits for like 3 or 4 hours. So these types of events happen. And they happen not just at solar maximum. As a matter of fact, this event happened as we were coming down to solar minimum. Our last solar minimum, not this one. But this stuff happens, it happens more frequently than people would like to believe. And the fact that we're so much more reliant on GPS than we ever used to be is getting frightening, right? Because now we're dealing with ADS-B. Those of you who are pilots or know about ADS-B, this is the satellite version of GPS, basically allowing planes to get their GPS signal from and use tracking from satellite GPS receivers instead of using anything from air traffic control on the ground. And it's a beautiful idea as long as it works wonderfully. And it wouldn't be such a big deal except for the fact that because GPS is so good, it's making everybody get a little bit more cavalier about how good the solution is and how robust it is. They're narrowing traffic lanes. In other words, they're squeezing the planes in closer together because they know where they are, right? So they don't have to have traffic lanes that are nearly so wide. So they're squeezing the lanes down and they're bringing the planes closer together in time. So they're actually creating a higher density of planes because they think that ADS-B is foolproof. And it's not. I mean, anybody who deals, who looks at this can imagine that if you're not getting signals from your satellites, this isn't just a ground receiver problem. And even if it is, who cares? The airlines are below the ionosphere. They're still going to have problems. So either you don't hear the satellites at all because the solar radio burst is so big, it's a radio blackout at GPS frequencies, or the ionosphere is getting so screwed up that everything's scintillating. So solar storms and solar radio bursts are problems for ADS-B. And we're going to learn that. Let's hope with no loss of life, but we are going to learn that the hard way. Anyway, this was the kind of the conclusion for, and I didn't write this paper. Last time, like I said, I talked about the authors who wrote this, and did this fantastic analysis. If you want more details about this analysis, please see my last course. But you can see they had fading signal to noise. That's what CNO means. They had fading during each burst, but lasting up to about an hour. There were multiple radio bursts because there were multiple flares going on. And they had positioning errors of up to 20 to 60 meters in the horizontal and vertical directions. Wow. I mean, that's pretty insane. Things are a little bit better now in terms of our ability to backtrack errors. The one thing that we can't do, however, is that if a solar radio burst is blacking out the communications so that we can't hear, a satellite signal. It's what I call the proverbial, cricket near the train track. You can hear the cricket. The satellite is the cricket, and you can hear its signal, chirp, 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 until the train goes by. And when you hear the train, all you can hear is the train because it's so much louder. Now, no doubt the cricket's probably still chirping, but you can't make that out because all you hear is the train. And then once the train goes by and everything settles back down, now you can hear the cricket chirp again. Well, the sun is the train, the cricket is a satellite, and there is no solution for that. If the train is so much louder than the cricket, it doesn't matter if the cricket's functioning perfectly, you're not going to hear it. And that's the problem that we have with our technologies here on the ground or even in the air that rely on satellite signals during a solar radio burst at the frequencies that you're trying to listen in on. I mean, it's just that simple. So that was that example, and I've got a couple more that I'm kind of still going through. Let's see. The sun sneezes, then ADS-B falls, and then crashes. Ouch. You're right. That's pretty much what that is. Is any of this going to be on the final? It will be if you are one of the people that in the Millersville University courses that I'm giving. Yes, this will be on the final. But for those of you who are helping me develop this course and are giving me great feedback like this, I can't thank you enough because you guys are helping me train meteorologists, TV meteorologists. So one day you're going to be watching a meteorologist, a very famous meteorologist potentially on television in your local community, and they're going to give a solar storm report, and you're going to go, I helped design that course. So you guys get kudos for that. So always smile in the future, especially when you start seeing people on the Weather Channel or people on the BBC or people even in in the United States and local news talking about solar storms, because most likely they got their training from Millersville University, which is what we're doing. So, okay, just looking at some of the chat here to see how you guys or if you guys have other questions. So activity increases in the next few years. We're going to have some big problems now as compared to 11 years earlier. Yeah, I believe so. I'm going to take a little sip here. I believe so. And if Scott McIntosh at UCAR is, he's the director of the High Altitude Observatory there. If he and his team are correct, they've got some of the most avant-garde research, I think, in terms of the solar dynamo from empirical relations and even just looking at much more than simply sunspots. They're looking at all sorts of proxies, potential proxies for the solar dynamo. And if their research is correct, we may be in for a larger cycle than we had back this last cycle. So, it's hard to tell. I think we're going to at least get the same, but it may be even larger. But thus far, it's definitely following a lot of the work that he and his team has done. They predicted that we would start seeing activity begin to increase near the end of this year, and it looks like that's what's happening. His team predicted that we're going to see the southern hemisphere, because of the asymmetry, the magnetic asymmetry right now between the northern and southern hemispheres. His team predicted that we'll start seeing the activity increase in the southern hemisphere before the northern hemisphere. That's what we're seeing. I mean, everything that he's talked about, his team has talked about thus far, we're seeing. So I have no reason at this point to disbelieve that he isn't on the right track. And there's no other team that I know of who has predicted anything close to this, who has been this correct, especially when it comes to magnetic asymmetry. And that's really the key with these very low active cycles or low activity cycles. So I'm continuing to pay attention very closely, and he's saying that there's a good chance he and his team are saying that there's a good chance that solar cycle 25 could actually be larger. So we shall see, you know. It's going to be an interesting next decade, that's for sure. Excuse me for taking a sip of water. Okay. Right now I have a dream to be a meteorologist in the future. I live in Germany, so probably not be in your course, but I would still give you credit. Oh, that's sweet. Guess what, SRG? No, you don't have to worry about that. We purposely have created at Millersville University, we've created this as a distance to learning, or just D2L program. The reason for that is the very first meteorologist who asked me to train them was from the BBC. I was over at the Mosswalk in the UK, which is the Space Weather Center at the Met Office. And I actually talked to David Brain and Andy Smith, who are now good friends of mine. And they specifically asked me, they said, we need to get training. The BBC wants us to get training for space weather. How do we go about this? And I was like, at the time, this was 2016, and I'm like, yikes, I don't know yet. And so that kind of facilitated me kind of getting off my bum and really start not just dreaming about the day when I would train meteorologists, but actually taking actions, taking real steps to try to figure out how to get there. And Patreon was a huge, huge help in that regard. I don't think I could have done it without all the patrons here. And so when we put this whole Millersville thing together, we decided specifically that we would have something that would be online so that people who are across the pond or, you know, in different parts of the world could still get access to the training, and they didn't have to be a person on campus. They could actually access it right there with themselves. They just had to enroll. So don't worry about it. You could very well become a student in this course or in this certificate program and learn. It doesn't matter that you're in Germany. We have anticipated that. And who knows, maybe by the time you're ready to actually get your training, there may be other teachers in other institutions who are doing the same thing. I'm hoping that, as I tease among my colleagues, I say, I hope that I can teach other people to do this and take over before I become space weather grandma. Because the last thing I want to be is space weather grandma with a walker trying to do space weather forecasts in my 70s or something. I'm not sure you guys would like that. I'm not sure I would like that either. So that the whole point is to try to get the new generations to take over and have this go far beyond me. So anyway, just a little humor there. Okay, let me go ahead and talk about the perfect storm with Hurricane Harvey. And Irma. This happened recently. This was in 2017. Again, we were at the declining phase of the solar cycle. Actually, let me step on this side. We were on the declining phase of the solar cycle, and we had Hurricane Harvey had just hit. Hurricane Irma was inbound, and we had region 2673 that grew into a nasty sunspot. If I go over this way, I think, yeah, grew into a nasty sunspot within just a few days of emerging on the surface of the sun. This is another thing that Scott McIntosh and his crew had predicted, was that during these really low activity cycles, when the sun's magnetic hemispheres are not working or not in sync, you get these really ugly active regions, and it means you can get really serious, really extreme events. So some of our Carrington class events have occurred because of these types of regions and during these low activity cycles. In fact, this region spawned a Carrington class event or a near Carrington class event that barely hit us. It just barely clipped us. It actually was fired on the backside of the sun, but it was so big it still clipped us and gave us a G1 level storm. It was insane, but it could have been much, much worse. But during this period of time, this ugly active region launched in a single week. It launched, and it looks like my text is blocked. It launched from September 3rd to September 7th, or September 10th, I think. It launched 4 X-class flares, something like 25 M-class flares. And these are at R3 to R4 level blackouts and R1 to R2 level blackouts. So we basically had radio blackouts for an entire week on the day side of Earth. And then it had 2 solar radiation storms, which I won't go into, and 2 geomagnetic storms that I won't go into. But all of that happening in a single week made radio communications horrific. And Irma was right here. barreling down Puerto Rico, coming up to the Keys. It decimated Puerto Rico during this period. And you can even see with the radio blackouts, if I go over here, down, 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 come on, over in here, you can see we were at like an M1, we'd get up to an X class level, so it was like an R3 level. We'd go down to an M1 level, to an R1 level, and then back up. So we would always be at an M1 or an R1 level for radio blackout or higher. And this right here, I think, is over only a 12-hour period. So it's just like, oh my gosh, or maybe it was a 24-hour period. But we had this for like a week where radio operators just couldn't get anything. Here's an example. This is from Nathaniel Frizzell from the paper that he did with HamSci. Here's just one example, and again, this is a review, so I've gone through this before. But here's radio propagation before a flare and during one of the flares. Look how much it drops out, you can see. And here's the flare that occurred on this side here. You can see what that flare looked like over the day side. And it was just absolutely horrible over a broad frequency range. These different colors are different frequency ranges. If you want more information, again, go see one of my earlier classes. But this was something that ended up being a nightmare for radio, for emergency responders. Even the Red Cross thought that the radio blackouts, that their satellite phones weren't working because of the hurricanes. They had no idea that their satellite phones weren't working because of the radio blackouts from the sun. Because satellite phones work on frequency ranges that are very similar to GPS. They're at like 1.4 gigahertz. And we were getting radio blackouts clear up to those frequencies. So guaranteed GPS didn't work, satellite phones didn't work, ham radio didn't work, and we had people struggling in these areas who had no cell phone, no power, and there was no ability to communicate with them during for almost a whole week during this period. Okay, so those are big events, but they're not Carrington class events. And as I start moving into the new stuff, I'll go ahead and just see if this will play over and over again. I'm not sure it will. If it does, it's just good, good background here. Some of the biggest, let me move over here. I guess it doesn't play over and over again. Some of the biggest events in our history are considered white light flares. These are the ones that have so much energy. The flares themselves have so much energy that not only can you see them in hard X-rays and soft X-rays and microwave, and you work your way down, but you end up seeing them in visible light. And that's great because obviously in the early days of space weather and even astronomy, when we're looking at our own star, having a white light flare means that you can see it with your, through your telescope that doesn't have any special filters on it or anything like that. You can actually see a flare occurring. It's a wavelength that makes it all the way down through our atmosphere, and we can see it on the ground. So white light flares were some of the first flares that were ever observed. As a matter of fact, the Carrington flare was a white light flare. It was the first flare ever observed, by Richard Carrington, as well as another person. I forget who it was, but there was another person who actually watched and saw this flare. This is, you probably have seen this diagram before. This is Carrington's actual diagram of that sunspot region. You can see it's very, very ugly. And when the flare occurred, he looked through his telescope, he could actually see the white light ribbons. So it says sunspot flare ribbons, you see where the arrows go? He's actually drawing the ribbons in white light that he saw. In other wavelengths that we see in space, those wavelengths don't make it down to Earth. They don't make it through what we call the atmospheric window. Our atmosphere actually shields out a lot of the extreme ultraviolet and higher frequencies from getting to the ground. So that's why we have to have so many telescopes in space, because otherwise we wouldn't see the way the sun looks in SDO. You can't see that stuff on the ground. That's why everybody thinks it's CGI. It's like, oh, well, the sun doesn't look like that. Give me a break. You guys are fooling us. No, it actually does look like that if you can see it in ultraviolet in space. But you can't see that on the ground because all those wavelengths are blocked. So the stuff that makes it to the ground then obviously becomes the gold standard, right? But as you can see, I'm beginning to set up the solar flare myth. What happens is that we become very myopic and very, very short-sighted, because we believe only what we see, right? I mean, we still have a whole contingent of people to this day who argue with us that SDO and all this other stuff, all these telescopes that we have in space, aren't real because they don't see it on the ground. And when you believe that what you see is the only thing that could possibly be true, then you end up causing yourself some major problems down the road. But the sad thing is that it's so human to do that, right? It's not just the average public, person, layman who does this, non-expert who does this. Scientists do it too. And so when we as scientists, even as Carrington started out and started drawing in flare ribbons and things like that, and then we got hit by something 17 hours later, we assumed that it was the flare that did it, because that's what we saw. And here is, this down here is actually magnetometer readings that actually went off scale because at the time we had never thought that the Earth's magnetic field could ever get that squashed and be that strong. We had no idea that it would ever do anything like that. And so when the actual coronal mass ejection hit that occurred during this flare, then we just attributed it to the flare. And that became synonymous. So when we talk about the Carrington event, right, we talk about the Carrington, the solar flare. We don't talk about the Carrington class coronal mass ejection. You don't hear people talk about the Carrington solar storm. You hear people talk about the Carrington solar flare. Okay? And that is the issue. So white light flares are fantastic. They are the largest events that we have in the historical record, but they also are the most misrepresented. So pretty much the solar flare, when it hit, yeah, it probably caused radio blackouts, but who cared? Back in 1859, I don't even know if we didn't really use anything like that, right? We had telegraph wires. So that's not going to cause a problem. But the solar storm was going to cause a problem when it hit Earth. But the solar flare, well, radio blackouts weren't really a big deal back then. So when we talk about it, it's definitely one of the largest flares to have ever occurred since telescope observations began. And it does have a classic signature. We call it a two-ribbon flare. And if you've watched the other classes, you know what a two-ribbon flare is. But really, everything that we talk about when it comes to the effects of that solar flare wasn't the solar flare. It was the coronal mass ejection that hit afterwards. Okay, so it sets up, and here are some of the examples. Okay, the Carrington event. So that's why you call it Carrington event, because it really wasn't a Carrington solar flare. It was a Okay, looks like am I back? I just got an error. Somehow it's raining here, and so we're having a little shoddy internet connection, and I'm hoping everything is back. Are we okay? Yeah, video jumped. I saw it. I got a big error on my system. Let me try to figure out what's going on. Hang on, guys. Hey, Kent, is Evelyn on? Everybody's hearing me. Is Evelyn on the internet? Can you tell her to slow down? Because my video just jumped on my class. Sorry, guys. It depends on what she's doing. She's not? Froze for a moment, reduced bandwidth. She is, okay, so my daughter is hogging the internet. She's playing games. So tell her to play a different game. Because right now we're having issues. Kids are playing video games, yes. Yes, don't you love live TV? Okay, so I'm going to keep that door open for just a second. If it gets too noisy, let me know. But really, when I go back to the Carrington event, and I'll stand over here for a second, this was the largest thing in 500 years. It was even larger than one of what we call the standard candle for solar events, which was the March 1989 event that caused the Hydro-Quebec grid to shut down, caused the Toronto Stock Exchange to shut down. People were offline. I mean, there were like 6 or 9 million people offline for many hours in Canada. There were a lot of issues that happened on that one, and this was even bigger than that. Here, the North American telegraph system failed. The systems functioned despite being unplugged. We had sparks. We had paper catching on fires. The operators were shocked. They were burned. I mean, I've gone back to some of the reports written up in books, and it's pretty insane how large of an effect it was. And I can go on and on and on. We had stuff clear down to the Caribbean, the Hawaii, and Singapore. We actually had the auroral oval from the top and the bottom. They met each other at the equator. It was pretty intense. Again, this is all solar storm related, not solar flare related. It had global impacts. Here's an example. I've actually, oh, wait, am I on the wrong side now? Yeah, I am. Oh, that's weird. I thought I was on the right side. Okay. I get on this side. So what you can see here, here is as you can see, map of the world. There in 3 different times. There were several different Carrington periods where we had this solar storm that intensified, quieted down, and intensified again. It may have been multiple solar storms being launched, because we did actually have multiple Carrington flares, but I think there was only one white light flare, and that's why Carrington we only talk about one, is because there were multiple flares, but there was only one white light flare that was recorded, that was actually seen. So everybody thinks there was only one Carrington event, but it's not true. Anyway, you can see in this map, you can see these are the lowest area, the lines are in orange and I think in yellow show the extent of what the auroral oval was at. And the lines, the reason why they're bent and stuff like that is because we're mapping onto geographic coordinates what geomagnetic coordinates are, so things are kind of bent and loopy. They're not going to be straight lines. But you can see the lowest extent, which is the orange line, that is how far down the auroral oval reached. And that means it was seen, the aurora was seen even lower latitudes than that, because you can actually see stuff low in the sky. You can actually see stuff further away than the actual latitude. And you can see that the orange dots, I believe, are the ones where there were actual active aurora reports at the time. And really what it means is that with the orange lines being really low and the yellow lines being really high, that's the extent of the auroral oval. So basically that entire thing, instead of it being a nice small oval where you have to look, if you're above it, you have to look south for aurora. If you're below it, you have to look north for the aurora. If you're in the northern hemisphere, the southern hemisphere, it's the other way. In this case, the auroral oval was so thick, it didn't matter where you looked. It covered the entire globe, basically. So aurora was really intense during this event. But again, everybody thought this was because of the solar flare. It wasn't. It was because of the solar storm. Now, here's another one. And this is an example that had happened recently. This is if anyone saw there was a recent paper put out in Space Weather by Dolores Knipp et al. Now, Dolores is a good friend of mine. I've served on committees with her, and I owe her several papers. She's the editor of the Space Weather Journal. But she wrote this fantastic paper that she took a long time, her and Brian and Peggy and Don, they took a long time researching some declassified documents from the American military that talked about basically sea mines that got detonated during another huge flare. This was back in August of 1972. Now, this was a Carrington class event. Let me, which side should I stand on? I'm thinking, no, let me stand on this side. This was a Carrington class event, and you can actually see the sunspot. If I want to go over here, I think, yeah. See the sun, see that dark sunspot? Look at that thing. It's huge, massive. Up here, that. And you can see the flare in the second panel. You can see the flare. Look at it. Okay, and there were several flares, and I'm going to stand right here and point to like right here, because I think right here you can see there were 2 flares on August 2nd, one on August 4th, and one on August 7th, all from this same region. Okay, but there were 2 white light flares, which tells you they're massive, massive flares. So these were very, very big events. As a matter of fact, I think I have, if I play this, see if it lets me play it. Is it going to let me play it for you? Yes, it does. Okay, here, let me get out of the way. I forget which way is going to get out of the way. Here is, on Big Bear Solar Observatory, you can see one of the flares that occurred. This is the state of the art for the technology at the time. This is, I can't remember if this is the gamma ray flare or this is the August 7th flare, so it was one of the white light flares, I believe. Here it is again. This is what we had to look at the sun with back then. So that is a massive flare. Do you see two ribbons? I don't know, I think I see just a whole, mess of stuff. So it tells you how incredibly intense this particular flare was. Let's see if it goes back. I have to go back. Okay, wait. Are we back? Yes, I think. Yes. Okay. So this was the active region. You can see it's just messy. It's just a whole ugly bit of stuff here. And all of it just lit up. And you had this huge filament down here at the bottom, right here. Oops, if I can trace it. This filament down in here is what went, you see that snake-like thing? This is the thing that left off. I believe it was lifted off and became the big solar storm that was associated with these flares, not causally, but the flares destabilized this region. This thing lifted off, and this is what caused a lot of the trouble at Earth. Now, granted, in this case, it was 1972, so we did have a lot of let me stand on this side now. We did have a lot of ability to track exactly what was going on, including HF radio disruptions and as well as the CME. But back then, in 1972, we were under the impression of the solar flare myth. This is written, these bullets are written from the point of view of now. But back then, we all thought it was just the solar flare that did this. So we had an extreme Carrington-class CME that hit Earth. On the 4th of August, we had a radiation storm that disrupted many of the spacecraft and their instruments, destabilized portions of the North American power grid. It rattled the Earth shield so much that it triggered sea mines. Back then, sea mines were set so that if a metal hull went by them too closely, it would change their magnetic field, and they had a relay that would trip. And so if you got a big change in the magnetic field, it would trip that relay and the mine would detonate. Well, the storm, the Earth's shield just rattling because of the solar storm hitting it, and the magnetic field shaking and changing direction, changing intensity, all of that stuff as it wiggled and thrashed during this solar storm. That was enough to trigger all these sea mines. So now you can see why, of course, everything was classified. Because they had to go repopulate the minefield. If you want more details about this particular event, I do talk about the CME that it was associated with back in one of my CME courses. Probably the second to last CME course, I believe I talked about it. And I went over this event in detail from the perspective of the coronal mass ejection. Now we're kind of talking about it from the perspective of the solar flare. Okay. One of the biggest things it had during the solar flare itself was the long duration radio disruption greater than 1 gigahertz. So there was a radio blackout once again from a white light flare that had a huge component that was above 1 gigahertz. If we had had GPS at that time, if we had had satellite phones at that time, if we had had ADS-B at that time, all of it would have been disrupted. All of it would have been global, at least globally on Earth's day side. And then we would have had to deal with all the disruptions from the CME that hit later on the night side of Earth. So this would have been a global disruption if it had been more modernized, if things had been more modernized. As it was devastating to the American military. Had no idea it was going to happen. Now, I probably don't need to go through this, but the flare facts, these are lifted straight from Dolores's stuff. If you want to know more about all the details, please see her paper. She goes into all of the solar physics aspects of it. You could see, of course, all from Mount Wilson, all the detailed analysis that was done there. And then she has all of this information in there for you, how the size of the filament, how it happened. The interesting part is when you actually, let me get out of the way here. I'm going to stand over here. When you actually look at the timeline of this flare, you can see that how, and the set of flares, you can see how many there were. It was just pop, 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 pop. So this thing is very much like the region 2673 that we had back in 2017, where for an entire week, the radio frequency noise, from this thing was probably popping off, you know, having radio blackouts just constantly. And you probably couldn't even get down past an R1 level before you'd pop back up to an R3 or R4 level, possibly R5 level during the big, well, definitely R5 level during these biggest flares. And it just was long lasting. If I look, it's the 25th through the 16th. I mean, that's the span of this whole plot. And the big flares started around, what is it, like around the 1st? So for 2 weeks, for basically the entire 2-week period that this region transited the Earth-facing disk, there was noise, right? Can you imagine that with ADS-B today? Having random radio blackouts for 2 weeks, almost nonstop? How about if you had an earthquake or a hurricane? Do you think we could handle that today? How about GPS? Anybody use Uber or Lyft, or, you know, might be a taxi driver? All of that stuff relies on GPS. So it would be awful to have these kinds of outages over and over and over again. Here's some of the flare forensics that they've reconstructed from this, and I'm trying to remember what it was. You have flux intensity, field intensity. I'm trying to remember what I really wanted to go into. They didn't have a lot of detectors back then, and the sad thing is that the detectors saturated at the X5.5 level. So they really didn't even know back in 1972 how big this flare was, how big the biggest flares were. But obviously, if it's a white light flare, it's going to be Carrington class. It's going to be, you know, massive. And obviously the CME that's associated with it will be massive as well. So you can see that this, just even in this plot here, the period of time that this lasted, that the intensity of these different, I think the different frequencies, flux intensities, yeah, HF radio, you've got different stations. You can see the disruptions were actually over many hours. So it was a multi-hour dayside radio blackout, and in a very slow recovery, trying to get back into decent radio propagation during that period. And more details are in her paper about it. But this was not a joke in terms of the event for this, and this is just one of the flares. This is the August 4th flare. Unfortunately, with these really old events, it's hard to do a lot of forensics reconstruction because there just wasn't that much instrumentation way back then, and because we didn't know what we were looking for. Back in 1972, we had only, for about a decade maybe, had agreed with Eugene Parker that, yeah, okay, maybe there is a solar wind. Because Eugene Parker was probably laughed at when he published his paper in the 50s about the solar wind. He was probably laughed at for a decade before people started to say, okay, yeah, you know what, maybe you're right. So we didn't even really, we'd barely gotten comfortable with the idea that there was a flowing solar wind coming out of the sun, and we definitely didn't know all that much about coronal mass ejections. Skylab, I can't even remember when Skylab was launched, but it was right around this time, right, the 70s? And so we were just getting the first views of coronal mass ejections and knowing that there were actually these big transients that lifted off the sun. For more details on that, definitely see my first class on CMEs, because that talks about the history of coronal mass ejection observations. And then, of course, we had a huge upper atmosphere disruption. You can see these are different, I'm trying to remember, these are different heights in our atmosphere, and you can see we had the atmosphere puff out when the solar storm hit. And what happens when that happens is all the low Earth orbiting satellites, they encounter a much higher drag than they would normally have, and it slows them down. Well, in orbital mechanics, when you slow a satellite down, it drops, it falls, and then it speeds up, because that's just the way orbital mechanics works. So imagine trying to track a satellite that not only is not as high as you expected it to be, it's now at a lower altitude, and it's ahead of where you expected it to be. Because when you go into a lower orbit, in order to stay in orbit, you have to be faster. Or orbits that are further out, like geosynchronous orbits, for example, they can move much more slowly. But low Earth orbits, man, they got to zip. They got to zip by. So when that happens, so when you slow a spacecraft down, it falls and then it picks up speed. It loses potential energy and gains kinetic energy, for those of you who are physicists. And that causes a real problem when you're trying to get communications from these satellites. And one of the nice things that Dolores talked about was that back in 1967, when we had a similar event happen, a similar solar storm happen, NORAD lost half its catalog of spacecraft in low Earth orbit because of this, simply because the atmosphere puffed out. And you may go, okay, yeah, well, whatever. That's what does that mean to me? And all I can look at that and say, Starlink, anyone? Because what is Elon Musk doing? He wants to put up 30,000 at least satellites in low Earth orbit. Have you seen these satellites? They've got albatross wings for solar panels. They're massive, right? And these, all I see on these tiny little CubeSats that basically have no mass at all I see are huge parachutes. And so when we get a big solar storm, just one, we only need one, what do you think is going to happen when this atmosphere puffs out, right? And you get huge changes in density, which is what you're seeing these big peaks are. Huge changes in density. Well, the neutral atmosphere is going to puff up, it's going to get denser, it's going to cause drag on these satellites, they're going to slow down, they're going to fall, and they're going to advance. So now half of his 30,000 satellites are going to be somewhere other than where he thought they were. Oh, and by the way, these satellites have to cross-link with lasers to talk to one another. So not only will the ground not know where they won't know where they are. Each satellite won't know where they are. So do you think he's thought this through when it comes to space weather? Somehow, we shall see. We shall see. But I'm going to be very tickled when we see how they ride through the first G3, G4 level storm that we get from some big event from this next cycle. Anyway, so here's a little bit more information about the Haiphong minefield. I talk about this in more detail in a prior course. But yeah, the solar storm was so strong that it rattled Earthshield so much that it caused 4,000 mines, over 4,000 mines, to be detonated. Just boom, all by themselves. Could you imagine back in 1972 not knowing what did this, and you think solar flare did this? Boy, these things are scary. And that's the attitude we had back then. Luckily, scientists are, we're slow, but we can learn. And so we do. We learn from our mistakes, and unfortunately, we learn pretty well, but then there are always, there's always this collateral damage. We put this information out, and we have maybe hundreds of years, if not thousands of years, of stories and documents and writings that we have to back up certain claims that then etch certain theories in stone. And when the scientists realize that they're wrong, it's easy enough for a scientist to go back and erase that in the scientific community. It's not so easy to do that for the public, right? For those who are not experts. And that's really where we start finding ourselves. So let me talk about that here. Let me shut this door. I'm hearing television commercials, and I really don't want to hear that. And some of the first hints that we had that kind of drew us in this direction were things called hydro flares. Now, I'm not going to talk about a hydro flare too much. I'm only going to show one example, and it's a strong example. It's not. There are a lot weaker examples. Actually, I'm going to show more examples than that. I forgot. But I'll talk about that after the solar flare myth. But one of the examples of a hydro flare is one that's actually quite well known, and I've got two different pictures behind me that show what that is, and I'll play a movie in a second. But to explain it, a hydro flare occurs when there really isn't a sunspot region. We've been talking about solar flares, and we've been talking about radio bursts, and we've been talking about how you have to have a sunspot, right? You have to have a magnetically active region. You have this nice loop thing. We'll talk about the standard model. We have the CME that lifts off, maybe or maybe not. But we have a very well-known set of observations that tell us exactly how flares work. And so we know when they will occur and what will launch a CME, right? supposedly. Well, what happens when you have a flare that doesn't occur with a sunspot underneath it? Well, that's what a hydro flare is. It doesn't happen near a sunspot region or an active region at all. It actually occurs, it's oftentimes just a filament that lifts off. Well, the filaments, which are these, snakes, if I can actually show you some of them, you can see them on this plot. That's kind of why I did this. This is actually a movie, which I'll play in a minute. But I'm trying to point to a filament channel. There you go. See this one that looks kind of like a horseshoe here. See that? I'm drawing I'm drawing too big of a loop, but with my finger. But there it is. That horseshoe, that is a filament channel, believe it or not. A filament channel is kind of like a region on the sun where the magnetic field kind of is kind of getting the plasma, it's kind of jailing the plasma, the solar atmosphere gases, in such a way that, and especially the dense stuff that sits down close to the solar surface, in such a way that it kind of forms it and traps it in like a tube. And so they call it a channel that creates a filament. And so you can have empty filament channels. These are channels that exist, but there's no plasma in them. And you can have full ones. When you have full ones, then you get a filament sitting inside the channel, and most likely it'll go unstable for whatever reason. And in the early cases of hydroflares, the filaments would go unstable pretty eruptively, and that's what this is, for example. They're still slower than normal, than a solar flare, than a typical solar flare that's explosive from an active region, but they take longer. They take maybe a couple hours or maybe a little bit longer. And you can have a double ribbon, and you'll see a double ribbon in this one when I play the movie. But they generally don't burn quite so brightly and not quite so long. So you're not going to get an X-ray burst, from a, well, you get an X-ray burst, but you won't get like an X-class flare. You won't even get an M-class flare. Usually these are C-class flares, sometimes B or A-class flares, and they're usually gently rising and gently burning. There's no impulsive burst because there's nothing really explosive. Now, I'm going to show you one that looks reasonably explosive, but it was believed for a long time that anything like this really couldn't cause a geomagnetic storm, cause a big solar storm at Earth. But they soon learned that, yes, actually they can. And that became part of this solar flare myth issue. This was part of it, and also something about the big solar radiation storms that come from these things. People believed that at the time that solar radiation storms could only come from solar flares. But there became some inconsistencies that caused a lot of head scratching, and it wasn't really consistent with how solar flares are thought of, and I'll get into that in a minute. But first, let me just play you this solar flare movie. Let me get the right place here. Now, I gotta make sure I stand away from it so I don't block it from you. So you'll see this, okay. You'll see it happens reasonably fast. You see that? I'm sorry I should have slowed it down, but let's see if we play it again. I might play it several times for you. Come on, play. Whap. See that? Now, did you see the two ribbons? Let's see if I can go over here. Let me try to do it one more time. I'll see if I can pause it right after it goes. There, pause. Okay. So it's paused. Now let's see if I can go over here with my two fingers. Well, I'll just do one finger. Come on, Tam. I'm watching a green screen version of this. So here's the two ribbons. Do you see them? Right there? And if I draw kind of down this way, there they are. See that? Those are the two ribbons. Okay, that's the two ribbon flare. They're on either side of that filament channel, and that CME just lifted off. But there's no active region right there. That's a hydro flare. This flare I don't think even was an M-class flare. It was around a C-class something. I don't remember what it was. And then I've got, if I move over here, so you can see the chronograph. See this chronograph? So you can see that CME coming out, right? It's pretty massive, pretty extensive. This thing actually did hit Earth, and it actually did cause a geomagnetic storm. But there was no real strong solar flare to indicate that that would happen. Now, back in the 70s, 80s, and even in the early 90s, people were arguing about these types of events that, well, they can't really cause, these are eruptive, you have eruptive flares, you have impulsive flares, and then you have filaments that erupt. But filaments really, they're not explosive. They're not really going to cause the trouble at Earth that big solar flares do. because big solar flares are the ones that are very eruptive, and the eruptive flares, as they called them at the time, there wasn't CME, they didn't care about CMEs. The eruptive flares were the ones that really mattered, because when it came to what we call geoeffectiveness, meaning earth effects. And so there became this frustration with the people who studied these types of phenomena, right? People like me, except I wasn't, well, I was doing it in 2014, but back in the early 90s, I was just beginning to get into the field as a graduate student. And so I didn't really understand what the hoopla was all about. I didn't realize that there was this big war between the solar flare people and these CME people, because the CMEs were kind of newcomers, right? I mean, we've had white light flares since the Carrington days. So solar flares were everything, right? And you had impulsive flares that didn't shoot CMEs, and you had eruptive solar flares that did. But it didn't matter, everything was a solar flare. And yet there was this class of coronal mass ejections that stood alone. And it was hard to reconcile. On top of that, we'd also have solar storms that had these radiation storms with them. And the radiation storms would last for days and days and days. But a solar flare would only last for an hour. So why do you get a radiation storm that keeps going? And so there was all this argument about how the radiation storm could possibly, be lingering or getting stuck in the ether, getting stuck in the solar wind and diffusing out and all this other stuff. But it just wasn't really, these were relativistic particles. They travel to Earth in an hour or so. Not much, doesn't take much longer than the speed of light. So how could they last for days? So what's driving them? How can the solar flare has been long over? So there were all these inconsistencies going on at that time. And it caused Jack Gosling to basically write the landmark paper of his lifetime called The Solar Flare Myth. I was very lucky to know Jack quite well. I became a grad student at UCLA right at the time that right before actually he published this paper. And because I wanted to study coronal mass ejections, and I was a UCLA person, and UCLA was running the institute that he was at in Los Alamos, he became one of my thesis advisors. He became what was called my IGPP thesis advisor. And I will treasure, he's no longer with us, he died last year, but I will treasure my time with him because he taught me so much. And his love for space weather was infectious. But he also was very savvy. And he wrote this landmark paper, and it infuriated the solar flare community, the solar scientists community, the astrophysicists and the astronomers, and as well as the budding space weather field. Now, space weather back then was not called space weather. In 1993, we didn't call it space weather yet. It was still space physics. Jack did interplanetary work, just like I did. We were people who didn't study a star. We didn't study a planet, so who cares? We studied the vacuum of space. There's nothing in there. There's nothing interesting there. Well, yeah, there is. There's coronal mass ejections. And he wasn't just trying to make a name for coronal mass ejections. He was trying to tell the solar flare community that they're getting the physics wrong. And they didn't like it. This paper was argued about for probably more than a decade. And in it, he basically said, we have two paradigms. We have the paradigm that we have right now. This was in the early 90s. Remember, we hardly knew that the solar wind had been blowing for more than a decade. So it's very easy to get confused about solar flares, especially when Carrington and everybody else have seen white light flares, and then we get an affected Earth. So it has to be solar flare related, right? And this was the paradigm at the time. We had the idea that you'd have a flare, and then you'd have all of this stuff happening over here. Well, actually, let me do this side first. All of this stuff happening over here, which is what a solar flare, that they knew, that we still talk about solar flares are, with particle acceleration, what am I saying? So, and something solar propagating to 1 AU, which is Earth. So you have a proton event, which means basically a solar radiation storm. You can have an absorption event once the radiation storm gets to Earth. You have the radio blackouts. You have all of that stuff with the flare, right? But you also have the heating, the material ejection, see all the stuff, the capitalized stuff. Then they have in the interplanetary space disturbance, which is what coronal mass ejections were seen coming out of the coronagraphs at the time. And then you'd have a geomagnetic storm and you'd have aurora. Believe it or not, back in the 90s, aurora in the scientific community was associated with a flare. So for all of you who are worried that, oh gosh, I can't keep it straight, geez, you know, oh, how horrible of me, I can't figure out the difference between a solar storm and a solar flare, how silly. Guess what? You're not very far behind the scientific community. We made a lot of mistakes early on, and it was all because of defining the science by what we saw. Solar flares came first. We had hundreds upon hundreds of years of solar flare observations. CMEs, we didn't see them. They're latecomers. We started seeing them when we launched, you know, we had OSO 7. That was in the 70s, maybe 60s or 70s, I can't remember. My very first class about coronal mass ejections talks about it. Goes through the history of CME observations. And it's fascinating, but it's relatively new. It's within the last 50 years. So, of course we'd get the paradigm wrong. So Jack took apart the paradigm and said, this is what we have. This is what we need. And look how much more centralized coronal mass ejection is in this paradigm, right? Do you think this went over too well? No, it really didn't. But he made some very compelling arguments, and I'm not going to go over all of this stuff, but see, you can see the coronal mass ejection stuff has not only the geomagnetic storm and the aurora, but it also has the proton event. So basically he took the proton event, the solar radiation storm, and the aurora, the geomagnetic storm, he took it away from the flare community and gave it to the CME community. He said, no, flare community, this isn't yours, this belongs to us, this is the stuff that affects Earth, and this is what matters. And the solar flare community freaked out. But he made some very compelling arguments. In the first one, let's see if I can stand. Which one do I want to do first? Yeah, I'll do this one first. So in this plot, what he's talking about here is, let me go to the second plot on this paper first, because you recognize this. This is the sun. It's the edge of the sun. Remember, 1993, we didn't have great art to do diagrams, so everything's in black and white and it looks kind of bad. But oh well. Here's a diagram of the sun, and here's kind of that loop that sticks out. See if I can do the loop. Yeah, that sticks out. That's that magnetic loop that's going to end up becoming the coronal mass ejection. So he's talking about how the flare is just, in this case, it's a one ribbon flare. It's just at the edge. See right here. I'm trying to point to it. That's where he's showing the flare. And he's saying, but we have some, in the top panel, he's saying we have some intensification in a precursor. And that intensification comes from this loop that's going to be ejected. And so when we see the precursor and then we see the flare and the way the flare then lights up and then goes back down, the pattern that we see for these eruptive flares really are highlighting that there is a coronal mass ejection about to be ejected, and that is what's traveling out. So he made the compelling argument that there's some fundamental differences in the physics. It's not just the same as an impulsive flare. You don't just have an eruptive flare and a non-eruptive flare. There is some other physics going on. Look at this precursor. Look at the way it evolves. And remember, back then, they didn't have all the frequencies of light to look at that we do, right? They didn't have SDO. They didn't, back in 93, we had Yoko, I think. That's about it. You know, we're looking at the sun do we have SOHO? I can't remember. In 1993, do we have SOHO yet? We might have. So we might have had EIT, we might have had some ultraviolet, but we only knew really X-ray stuff. We didn't really know all that much in terms of ultraviolet, you know, extreme ultraviolet and some of the other frequencies. We definitely didn't have SDO that we have today, which is all the eye candy that I stand in front of, right, when I do my presentations. So we knew very little yet about coronal mass ejections, how they evolve, how they're launched, and how they differed from flares. But Jack decided, look, there's some fundamental different physics going on. And so he talked about that just in the terms of how the flare evolves on the sun when there's a coronal mass ejection involved. Because there's some precursors and there's some different behavior, and that's indicating that there's something going on moving outward that is fundamentally different than just the flare, the source of the flare on the sun. Then on top of that, let me stand on this side. Then he made another argument, and this had to do with the solar radiation storms. He said, look, you have a solar radiation storm that, if it were just flare particles, because there are radiation what we call solar energetic particles that come straight from the flare source. There's no doubt. There's what we call a seed population. It comes out from the flare source. But if it were just that seed population, then it would hit Earth maybe within an hour or so of the flare, of seeing the flare light. And then it would die down within probably another hour or two. Right? Maybe a little bit longer, but certainly not last for 5 or so days. He said, but with coronal mass ejections, and he's showing here in the sun, if I can point to the right place, here's the sun down here, and then you can see this big coronal mass ejection that comes out. See the big loopy thing? That's the coronal mass ejection. He's saying the solar flare particles, the radiation storm particles, are actually in a very large extent going out. And they're going out not because of that tiny little thing on the sun, but because of this huge shock driver in front. The shock is driving these big particle events. And this is something I will get into in my next set of classes, because what I'm going to talk about is going to be solar particle radiation. These are going to be radiation storms. That's going to be the next thing I'm going to go into. So we'll talk more about these events and how the shock drives them. But he's saying that if it were just simply that you had a solar flare driving these events, not only would they not be so long-lasting, but they also wouldn't be so large in extent, because we had several different spacecraft that would view the same solar, radiation storm from all these weird angles, from all over the place. And it's like, well, wait a minute, this spacecraft here didn't even see that solar flare. How come it's getting hit with a particle event? How come it's seeing the radiation storm? And Jack was saying it's because it's not being driven by the flare. It's being driven by the coronal mass ejection. So he made some very compelling arguments and had a lot of conversations with people, which led to one of the solar particle people, Don Reams, who is like the guru. Well, I can't say the guru, but he's really good. He's written a few really amazing review papers on solar energetic particles and talks especially about their spatial extent, how you can even, for example, identify when you look in the data. If you look and you see a solar particle event, you can look at the profile of that particle event in time and know which side of the sun the source region was, or which side of the sun, which side of either east or west it is from you, simply because the profiles will look different. And he's done so much work, and he was one of the people that Jack actually thanked in his solar flare myth paper, because they had a lot of good dialogue. He and Nancy Crooker and oh gosh, there's so many people. He thanks so many people in his acknowledgments, and I'll get into that in a few minutes. But here's the funny thing, and to see if I can stand by here. When Don wrote this paper, he had to deal with the fact that everybody was in this solar flare community, and he was part of it too. But look at some of this stuff from this dark side of solar flare myth that he wrote in response to Jack's paper. It says here, in one case, I think I'm going to try to read this. It says, this declaration of independence from the flare community certainly erased the attitude of benign neglect from the interplanetary phenomena and observations. In one case, it produced hostile dismay that Jack Gosling and a few of the other revisionists, can you believe this, would wage an assault on the last 30 years of solar flare research based on the low-grade optical data that the CME people use. If this isn't a war in the scientific community, I mean, take your knives out and just, this is how scientists argue. They argue in print, right? They don't argue, they don't go out and battle with their swords. They duel with their fountain pens. And this is exactly the way it happens in the scientific community. And this is one of the biggest wars that has been waged, I think, in probably the last, maybe of all time in space weather, was the solar flare myth. I mean, Jack was already saying a lot when it comes to, just titling his paper "The Solar Flare Myth." That's a big deal in of itself. But he absolutely waged war. And then I'm trying to see what the bottom one says here. Let me back out of the frame and see if I can read it. The motivation to distinguish flares and CMEs goes far beyond semantics. The terms flare evokes the idea of limited spatial and temporal extent. We will see that this alone causes serious errors when flares and CMEs are not distinguished. So he was talking about, again, the SEP concept, the solar radiation storm concept. He says, thus I speak as a former disciple and victim of the solar flare myth. Flares also imply, and then it goes into more stuff that's based on space physics. But it's very funny. He immediately jumps in and talks about this. And he and Don, Jack was already a really respected guy. Don is another very well-respected guy. And the fact that these guys were having to argue the case over and over and over again spoke volumes. And it literally has taken, it took probably a decade for the solar flare myth to really kind of dismantle all of this stuff. And here's some more of what Don Reams was talking about. He says, an assault on solar flare research. And he has to go back and say, hardly. This isn't an assault, guys. Don't be so angry about it. It's not that big a deal. But what the worry was that flares are going to be less interesting because they're not geoeffective. See, am I standing on the wrong side now? Let me stand back over here. That was the big problem, was that if you're going to steal if you're going to steal the Earth impacts from solar flares, meaning the aurora, right, and you're going to steal radiation storms, and those are huge impacts at Earth. Back in the day, radio bursts weren't really that big a deal yet. We didn't have all of the satellites that we have in space, and HF radio was still kind of more military than anything. So it wasn't considered. It wasn't a mainstay as of yet, and we didn't have GPS really. We didn't have things that solar radio bursts from solar flares affect a lot more now than they ever did. Back then, it was all about aurora and radiation storms. So the solar flare community thought their thunder was going to get stolen. And so they were very, very angry, to say the least. And in some of this stuff, it says, should CMEs be distinguished from flares? Absolutely. And this is where Don said something really cool. He said, let's see if I can get away from it. It says, this is like saying, by trying to keep CMEs and flares the same in a single thing, it says, this is like saying that since gravity causes rain to fall and the Earth to move around the sun, so gravity causes rain to fall and it causes Earth to move it around the sun, we should learn about meteorology by studying planetary dynamics. I mean, I thought that was a perfect analogy. It's like, no, just because they're related doesn't mean that they're the same physics and that you can learn about one by studying the other. And when you start talking about it from that point of view, you really start realizing, okay, as a scientific, as someone who's into scientific inquiry and scientific truth, you really have to start giving Jack his due, even though it may disrupt everything you've ever thought you knew about solar flares. And then, let's see, okay, and then he goes into the dark side of the solar flare myth, and this is the side that they really couldn't get away from. Let me stand on this side. It really was about the solar radiation storms. They could not reconcile the fact that these solar radiation storms would last days upon days upon days. And then the solar radiation storms actually, as soon as the CME hit and the shock passed Earth, the solar radiation storm would die down. And to this day, we see that. You'll have a solar radiation storm build as long as a big solar storm is headed toward Earth, and as soon as that shock front from that solar storm hits the planet, all the radiation begins to die down, and it's gone within a day or two afterwards. So these were things that they just couldn't reconcile because they were correlated with the coronal mass ejection, not with the solar flare. And it really became an issue for them. Let's see. So then he says, one of the difficulties in the present controversy is that flares and CMEs often occur together, but however, one does not cause the other. And how many times have you heard me say exactly that? The reason why space weather is so complicated and why the phenomena are so hard to separate is simply because you don't get one thing. You don't get one type of phenomena. You don't get just a solar flare or just a coronal mass ejection or just a radiation storm. You get the whole zoo all together all at once. And so it really makes it difficult to separate out what the different phenomena are and how they're going to affect you. And that has really been one of the hardest parts for me in all of these courses. So here was the conclusions, and I thought this was fantastic. So I'm highlighting it. But this is really the crux of the solar flare myth, that as long as the flare myth persists, it continues to cause a major misunderstanding of physics, of solar interplanetary and geomagnetic phenomena. After 30 years of such mistakes, it's time that we acknowledge the importance of the independent existence of CMEs and correctly identify them as the source of the dominant traveling interplanetary shocks, large SEP, that's solar radiation storms, events, and major non-recurrent geomagnetic storms. Those are the big solar storms that hit Earth. So, you know, we have it in the scientific community. Here's Jack. This, in case you want to know what he looked like, here's Jack. Or this side, sorry. This is Jack, not that. This is Jack. Very good friend. He passed away in 2018, and he was just a very funny guy. I'll tell you a quick story about him. One of my colleagues was giving a talk, or he was watching a talk and sitting near Jack. He was near Jack. I can't remember anymore if it was his talk or if it was someone else's talk. And Jack, because he knows energetic particles so well, it was a talk about energetic particles. Jack, because he was he knew this material so well, he was snoozing in the front. He was getting up in years and oftentimes would snooze in the front row. He had hearing issues, so he always had to sit close. And so he was kind of snoozing a little bit while listening to this talk. And in the middle of the talk, he woke up kind of and looked at whatever was on the screen and went, "Energetic particles up the wazoo!" and then went back to sleep. So he, you know, even in his dreams, he was being a jokester, he was being funny, and he was dreaming of energetic particles and the whole CME thing. He is very beloved in our community, and I am so honored to have been a friend and to have him as one of my thesis advisors and mentor. You know, I could go on forever because there's so many funny anecdotes about him. But one thing I hadn't appreciated until I looked at the solar flare myth again was I decided this time to read the acknowledgments, and I didn't keep all of the acknowledgments here. Oops, let me go on this. I'm going to stand in front of Jack for a second. Sorry, Jack. So I can read the acknowledgments. But one thing really struck me this time as I read his acknowledgments at the end of his paper. Now, below all this stuff that I blacked out here, he has like this huge list of people that he thanks, and I didn't add that, not to be disrespectful, but because I wanted to end on the note that I'm about to talk about. One of the things that this community, you guys, have helped me understand is how incredibly pervasive the cultural opinion is, the pop culture impacts of space weather are on how we frame our relationship with space. And it's a field called astrosociology, and it's becoming a real hobby of mine. As a matter of fact, in the Millersville courses, I'm going to be teaching aspects of astrosociology as they relate to space weather, because it's imperative that these meteorologists understand what they're up against. There are a lot of misconceptions about space and space weather phenomena, especially solar flares. And as you can see, there's that same kind of misconception in the scientific community. And as I read Jack's acknowledgments, down here near the bottom, I mean, well, we're first, basically at the top, he was talking about how he was inspired to write this paper. What really, I guess, was the straw that broke the camel's back. And it was a large AGU exhibit. This is American Geophysical Union exhibit that was prepared for the NASA Museum, the Smithsonian. And this was titled Electric Space, Our Sun-Earth Environment. It did not have a single thing about coronal mass ejections, and yet it talked all about the impacts of solar phenomena on Earth. And it's like the largest impacts are coronal mass ejection related. And the fact that it at the time it had such a big misunderstanding and such a big misconception just drove him crazy. So I guess it was the straw that broke the camel's back. And he says, further inspiration for the paper has come from statements made or not made in a variety of scientific papers, books, in scientific presentations, seminars, and colloquial, in casual conversations, in educational materials released for popular consumption, and in the popular press. And I said, son of a gun, he's talking about astrosociology. This is exactly what I find that we are fighting. There has been so much, and I talk about Hollywood media all the time, not just news outlets, but also Hollywood, right? All the books that are written and the movies that are made, they talk about solar flare disasters. They talk about space debris disasters. They talk about all sorts of things, but they don't talk about radiation in space. They don't talk about coronal mass ejections hitting Earth. They don't talk about half of the things the way they're supposed to talk about them. And it's lulled us all, scientific community and the public alike, into really not understanding what space weather is, or even that it exists at all in many cases. When people think about space and let's write a story about space and the hazards of space, people go, oh, it's the dark vacuum, it's the psychological, aspect of it. It's you'll go crazy, you're isolated, you're away from home, there's no air, you feel abandoned, there's all these things. But there's not space weather, because nobody even knows that space weather exists. And even in the scientific community, Jack found astrosociological issues that he tried to address. And so I feel really thrilled to be able to carry on, in a sense, the legacy of the solar flare myth and dispelling it, not just in my science, because I'm actually doing some of that, and I'll show you that in a second, but also in doing what I'm doing with space weather broadcasting. And I had not appreciated that until just last night. So there's a new way for me to appreciate Jack. He's always been an inspiration to me. And I can't, this is just one more thrill for me. And here's one way in my science that I've actually been dispelling the solar flare myth even more than it was before. This is basically the end of end of hydroflares, right? I showed about hydroflares, how they happen without an active region. Well, here's hydroflares in the lowest limit possible. These are hydroflares that if you don't look for them, you don't even see them. These are barely A-class flares typically, and they're not even near, they're filament channels, but a lot of these filament channels are hardly filled. And where they happen, the driver that seems to be helping them erupt and erupt incredibly slowly are coronal holes. But if you're not careful, you don't even see them. So I'm going to show you a couple examples. And this is what we've come to know as stealthy CMEs. You guys know, those of you who follow me on Patreon or some of my other science, you know that I'm working with stealth CMEs because these are the ones that NOAA and SWPC oftentimes don't even see and they can't even predict. But these do cause solar storms at Earth, and it's definitely not flare related. So let me show you a couple. Let's see. So here's one. Tell me if you can see this thing. Can you see where the flare is? Did you see that? I could turn around and do it again. Here, if I can get right there. Oop, I've got to go find me. Let me try one more time, guys. That's the only bad thing about what I'm doing. Right there. Do you see it? There's just a little bit of a change, but if you weren't paying attention, you wouldn't see it. And that caused this partial halo. See it on this side? And this did hit Earth. Here's another one. Let's see, I'll have to back up. Let me see if I back up this way. Make sure I can back up the right way. Yeah. Here's a second one. See if you can recognize this. It'll be up here. Whoop. Where is it? See, even I can't even see it. For goodness sake. Let me try it again. There it goes. Okay. Yeah, it's on the edge of this coronal hole. On the southern edge of this coronal hole one more time. I think let's try it. Come on. You gonna play? There you go. Hopefully I can point it out to you. Right there. Hardly saw it, right? Here, I'll skip to this last one because it's my favorite one. It's probably the easiest to see in this situation. So this is the one. Whoops, I have to get over here. Let me get close to it. And okay, it dropped off. Okay, try it one more time. Look at the southern coronal hole. Come back. Okay. Look at the southern coronal hole. Now look at this west side of it, or the east side of it. Watch this little thing disappear. See it disappear? Crazy, huh? Watch it one more time. Okay, watch it disappear. There it goes. See it disappearing? That caused this CME down here, and it actually caused a G2 geomagnetic storm. No flares, not even a recognizable X-ray signature. If Jack had had these examples of stealth CMEs back then, the solar flare myth paper would have been even easier to write because he would have had even bigger reasons to say, look, there are these things that occur. Now, there's no solar radiation storms with these, but there are big geomagnetic storms that can occur with these. And in this case, it's like the driver really isn't even a full filament channel that's being disrupted, but rather a filament channel that's next to a coronal hole. And the fast wind coming out of that coronal hole is somehow, I don't know, destabilizing that region because the edges of coronal holes are very tenuous and they change. So there's all sorts of really cool stuff going on. But this is one of the ways in my science that I'm actually helping to continue to dispel that solar flare myth, not only in my own community, but also in the public eye. And it just gives me great pride to be able to say that I'm, helping. I feel like I'm still helping Jack in one of the landmark things that he had always pushed for, and he will always be known for that paper, the solar flare myth. So, anyway, before we go into the last bit, which is planetary radio emission, I'll pause here and see if you guys have some questions, and I may drop off camera for a second so I can scroll back through the comments to to find out what you guys have been asking. So let's see, what is causing it to disappear? If you're talking about that the coronal mass ejection, the stealthy CME, it may be drag. We're still trying to figure out what the mechanism is behind it. There's something called interchange reconnection, which is a magnetic field reconfiguration. And because in coronal holes, all the magnetic field is what we call open, meaning it's not attached by both ends. It's not a loop connected to the sun on both ends. It's open. One end is open, so it's only attached on one end. But the closed magnetic field, which is the filament channels, they're all closed. And so if you get to the edge of that coronal hole, you have open field on one side, closed field on another. And if that hole is kind of eroding, you may have some of these loops that are being torn just simply by that coronal hole getting larger or changing. And it may destabilize that region and allow a filament to lift off, allow a stealthy CME to erupt over 12 hours. Because it's a very slow erosion and a slow mechanism that pulls these things out. And so it may actually have something fundamental to do with the coronal hole and the fact that the filament channel is next to a coronal hole. In most cases with these stealth CMEs, that's what we're seeing. Some cases it's because they're really high in the atmosphere, but other cases in the majority of cases it's because they're really close to coronal holes, and we think that that has something fundamental to do with the mechanism of how these things erupt. So these were things that back in Jack's day, we never even knew, we never even thought of. So it's really due to SDO that we're being able to see these a lot better than we ever have. So let's see. Okay. Hello, Miss Sunspot. Cute. Contact me and I can help you with a video display so you can seamlessly negotiate what side of the screen you need to stand on. Yeah, I don't have, this is being run out of my home studio, and I don't really have a huge budget for really cool, you know, flashy flip screen stuff and all that. I'm doing this off a Sling Studio, and so I'm looking at my controller, which is an iPad, and I'll show it to you so you can see what I'm talking about. There's my controller, so you can see I'm kind of running it off of that, and so it's not, you know, it would take a lot, I think, to change this, and the price point may be a bit too high for me, unfortunately, as of yet. But I'm definitely willing to talk with you about it. You know, it all depends. Okay, let me slide back through the comments and see if anyone has any questions, or if you have new questions, ask me now, because then I'm going to just talk about planetary radio emission, and then we'll just begin to really just take some final questions. Let's see. I find in satellite and fiber comms there is no appreciation of CME events and the predictive precursors we can see in comms anomalies. I agree. You know, the sad thing is the reporting of solar storms when it comes to fiber comms, and even when it comes to satellite communications, it's the only stuff that's ever been done really is behind, you know, closed doors, proprietary or with the military. Nobody really wants to have that stuff out in the public yet. But they're going to lose that battle because this stuff is becoming more important to the public, and the public is using a lot more, you know, a lot more information, and they need a lot more through fiber. They need a lot more data being transferred, and space weather is just something we can't afford to ignore anymore or keep under the rug. So, okay, let's see. I am not seeing a super lot of questions here yet. So if you have a really strong question, I'm trying to go through some of these. Let's see. So how does a Parker Solar Probe add to the science of space weather? Oh gosh, boy, I could really talk about that one. I will talk about that at the very end if you don't mind, because that I could go off on that forever. It's going to change. It's changing already. Oh, thank you, Jack. R.I.P. Parker Solar Probe is changing our fundamental understanding of how we perceive how the solar wind works, and how the sun creates its solar wind, and how the corona is heated. So it's a big deal. Let's see. What is the impact of space traffic management? What is, Harvey? Which question? What do you mean? What is the impact of space traffic? Are you talking about solar radio bursts? Are you talking about coronal mass ejections? Which phenomenon are you talking about? There's huge impacts to space traffic. One of the reasons why I'm trying to create a space weather broadcasting field is simply because we've got aurora tourism right now that's trying to get off the ground. And we're going to be having these, what are they calling them now, civil astronauts, going up not on the ISS, but, you know, up through Branson's thing. We're going to have them up in balloons at Worldview. Nobody's going to want to be going up when there is a solar radiation storm going, because you'll get 10 CAT scans in 20 minutes. That's nuts, you know. And you won't have the shielding that you will have when you're shielded in water, you know, with water. Let's say on the ISS, all of the astronauts go to the central core of the ISS that has a big, you know, is where all the water storage is. The reason for that is because they can duck under there, stay there during a big solar radiation storm, and not all of it, but a lot of the radiation is being absorbed by the water and not being re-radiated. The problem that we have with moon colonies or space tourism and you know, anything that, and even hotel ISS, is that when you have these big metal containers oftentimes the metal itself, if the radiation is strong enough, the metal itself of that container becomes a source of X-rays, of bremsstrahlung radiation. So you could actually get the container that you're in that's supposed to be protecting you. You could actually have that be more dangerous than the source particles themselves. That's something that's not really well known in let's say astrophysics, right? People don't realize that, but when you go into applied science and applied physics, and you're trying to, and nuclear physics actually, and you're trying to understand how radiation, damages materials, or how it penetrates materials, or stops in materials, and changes things, changes their nature, you learn all these hard lessons, and that is part of the problem with some of the satellites that we've built. Is that you can only design in so much shielding before the shielding itself becomes a source, and you end up causing your radiation environment to be worse. We don't have a good solution for that. So water is a great solution, but water is not easy to keep contained in space, and it won't be something that civil astronauts will use. So there's a lot of aspects of space weather that when you start getting civilians up in space who really don't know what they're signing up for, you can have a lot of trouble. Well, that's what space weather broadcasting is trying to, I don't want to say mitigate, but inform, right? It's just like terrestrial weather. People didn't understand necessarily how bad tornadoes were or hurricanes were until weather broadcasters were able to tell them, this is what you're in for. And it's not that it made any difference in terms of what you're able to do, or it didn't make any difference in terms of mitigating the problem, but except for it allowed people to make their own informed choices as to when they were going to go, what they were going to do, if they were going to evacuate or stay, that type of thing. And I'm trying to do the same thing for space weather. So, we may not have solutions for a lot of these problems. The problem may be to ride it out, but at least we can make better choices, at least from the public point of view. We can make better choices as to when we fly, or when we go up in space, or when we mine that asteroid, or when we go to Mars, for example. Mars that's another decent example. The worst time to go to Mars is now, while we're all trying to go to Mars, because Mars is close to Earth. It's going to be as close as it can be to Earth, in the next 20 years than it will be for a long time to come. Problem is, at least the window that we're getting right now is right at when we have these low activity cycles. So there's a lot more cosmic rays that are hitting, or that are coming and penetrating into our solar system. So that becomes a big problem. It's not really a great time to go to Mars, believe it or not. But, these are things that, as a space weather scientist, I'm trying to educate the meteorologists to understand, and then educate the public to understand. And then everybody can make better decisions based on the new knowledge that they have, instead of the knowledge that, all the misconceptions that Hollywood and everyone else has had us deal with for hundreds of years. Well, Hollywood hasn't been around for hundreds of years, but you know what I mean. Pop culture has kind of saddled us with. Okay. Do you need a force field to deflect the radiation? Oh yes, yeah. Let's put a magnet in front of Mars and have it create a magnetosphere that then will shield Mars from everything. It's not how it works. Believe it or not, energetic particles come up from the tail. So if you put a big magnet in front of Mars to create a protective sphere, a magnetosphere in itself, a magnetic shield, that shield will extend over Mars, but the tail of it will extend over Mars. And how radiation storms, for example, come up and actually penetrate those types of how they penetrate those types of magnetic shields is that they actually enter through the tail, because the tail is open. So Mars will still be bombarded. It'll just be bombarded from the backside. Instead of being bombarded from the front side where the sun is, it'll just be bombarded from the backside. Not much better. So there's a lot of issues, and a lot of people come up with all these really radical solutions. Dipole field is not really a great solution for a spacecraft or a planet in terms of creating a shield. There's still lots of holes, so to speak, that the particles and that these energetic storms can get through and cause issues. Basically, for Mars, colonies will have to be underground. That'll be the only way that they'll survive cosmic ray bombardment, and as well as solar energetic particle bombardment. You won't have Matt Damon hiding behind his little potatoes on the surface. It just won't work. So, again, education is required. So, okay, okay, so what I think I'll do now is I will go ahead and talk about planetary radio emission. Now, let me take a sip here. Now, I've only got a couple more slides before we're done. So those of you who aren't into the planetary side of things and don't really care how loud Earth is relative to other radio environments, now's a good time to check out. But I've only got a couple slides left, and it is actually quite interesting. And I don't go into it in too much detail because this isn't my forte. My forte is more the sun and Earth effects, but I do know a little bit about this stuff. So I just put this the typical radio emission mechanisms up, just to kind of remind you of the different types of radio emission mechanisms. So how the sun or planetary objects scream. As I take another sip of water. So we have plasma radiation, which is mostly the radio bursts that we see through the interplanetary medium. But we do get some coronal radiation that way too, but type 2, type 3 bursts, those types of things. Cyclotron maser, these are the ones that you will see these in planetary radio emission. AKR, you get this at Earth as well. I talked about this in, I think, the second course, maybe even the third course on radio bursts. I talked a little bit about this, especially AKR. Once the solar storm hits Earth and goes inside the Earth's magnetic shield, you get all of this low energy, low frequency radiation, or radio bursts, and I actually show a plot that talks about that. The synchrotron radiation, the cyclotron maser is one of the major ways that the Jovian system does, basically screams in radio noise. But we also have synchrotron radiation, and then of course thermal radiation, which is some of the lowest energy. And so the last three are the ones that kind of dominate when it comes to planetary emission. So it's planetary or planetary system emission. And so when I talk about that stuff on this chart here, you'll see what I mean. So can I stand on this side? Let me stand on this side. Okay, so here's a plot of planetary radio emission. You can see frequency down here on the this axis, from 10 kilohertz all the way up to 100 gigahertz. Okay, we're not saying 100 gigahertz, but up to 10 gigahertz, let's say. All right, and then you've got the intensity going up on this panel, right? And for any of those people who have ever said, oh, the Earth is so loud, we got television, we got radio, we got satellites, we got all this radio noise, my gosh, we're probably signaling every alien from here to Timbuktu, well, Galaxy M45, I don't know, from Arcturus on in, they've got to be hearing us, and they're going to be coming for us, and oh no, what are we going to do? Don't worry about it. Yeah, we may have radio emission that, that may be coherent, and there are a lot more periodic signals, but we are definitely not the loudest thing, even in our own solar system. You can see Earth, see the curve here that shows Earth. Let me point over here. You can see Earth, see this curve? I mean, it only goes about, what, that high? Yeah, look at that. We're not the loudest thing out there. We may be louder than Neptune, we may be louder than Pluto, we may be louder than even Mercury, and Uranus. But we're not louder than the two gas giants, not by a long shot. We got Saturn, that's got a broader band emission than we do, from 100 megahertz up, or what is that? No, from 100 kilohertz up to 1 megahertz or so. And then look at Jupiter. By far the loudest and most broadband emission comes from the Jovian system. And you can see it here. I mean, look at this. Everything from about 10 kilohertz on up to, we're talking, getting not quite, maybe 50 megahertz. That's a huge thing. And there's even some synchrotron radiation at low levels, but more thermal and synchrotron radiation from the Jovian system that Earth doesn't have. But we're talking orders of magnitude. Now remember, up on this axis, as you can see here, these are orders of magnitude change. So times it by 10, right? This isn't just a times 2, times 3 kind of thing. This is orders of magnitude. So the Jovian system's incredibly loud, especially their their AKR, their decameter radiation. And if you're interested in details of this work here and some more of the work, look at these authors. You've got Carr. These are some of the more ancient authors that have done it. But you can get even more details with some of the astrophysical phenomena that are going on with all the search for exoplanets. This is where you start really getting into, you know, the search for habitability and all that kind of stuff. They're looking for systems that have certain types of radio noise. They're trying to identify planets this way. And I don't know how much success they're having because astrophysics is not my field, once again. But it's definitely worth taking a look if you're interested in this, because planets and their systems do put out radio emission. Now, why is Jupiter so much higher? Well, if anybody who's looked at the Jovian system, here's why. You know, I think Saturn has something like 30 plus moons. Jupiter, I think, has less moons than Saturn. I forget how many moons Jupiter has, depending on how small, the smallest of the moons, if you count them as moons or not. But Jupiter has quite a few moons. And I don't know, I'll show you a plot of the aurora on Jupiter in a second that shows you some of the biggest moons like Europa, Callisto, Io, and Ganymede. You can actually see the footprints of those moons in the auroral pattern on Jupiter, on the caps of Jupiter. But the Jovian system, one of the things that makes it extremely unique, even more unique than Saturn, believe it or not, with all its rings and a couple of its moons having magnetospheres, is that the Jupiter system, the Jovian system, not only is there a huge amount of radiation in the Jovian system, and not only is Jupiter a differential rotator that then has just and rotates incredibly fast, so its magnetosphere, its magnetic shield is rapidly evolving, but it's got a veritable buttload of moons that also have their own magnetic systems. You've got Io or Io, depending upon how you want to pronounce it. I think the British always call it Io, so I call it both because I've been taught by both. So depending upon whose work I'm thinking of, that will dictate which pronunciation I use. It's horrible. Thank you, Bob Strangeway and Debbie Huddleston. You guys are, you know, I'm always going to be thinking Io because of you. So you've got Io or Io, its magnetic system, which is by far the loudest because of all the volcanoes on that moon. It's created what's called the Io-Taurus disk. You've basically got in its orbit around Jupiter, it's spitting off junk all the time. Mostly sulfuric acid, you know, various, you know, H2S, sulfuric, SO2, SO3 minus, you know, all sorts of junk. And it's leaving this cloud of charged dust in a ring, all in its you know, nearby its orbit. And because it's also magnetically connected to the planet itself, this ring has gotten kind of smeared out because all of the particles are charged that spits out of the atmosphere. None of it stays neutral. Nothing is neutral in space. And so because of that, these particles get charged as soon as they leave the atmosphere of the moon, and then they see the magnetic field. And because they see the magnetic field, they begin to spin and spiral and gyrate and do all sorts of weird, what we call bounce patterns inside the Jovian system, all in and around where Io's orbit is. So that is probably the loudest of all of the things, all of the sources of radio emission, and I'll show you that with this plot here in detail. But you also have Callisto. I believe Callisto has a magnetic field. Ganymede has also an intrinsic magnetic field, and Europa, I think Europa does too. I forget, sadly. It's been a while since I've read up on them. But I think all of those moons have their own magnetic systems, and they're all connected to the bigger host planet and its magnetic system. So they're all kind of tethered to one another. And by doing that, it tethers everything. It tethers their atmospheres, it tethers their you know, magnetic shields, and it causes them to have all these different wave processes that then can create these plasma emissions, these types of cyclotron maser emissions and all these other types of things that create radio noise. Now, in the case of Jupiter here, you can see at 13 centimeters, so these are two different radio wavelengths if I show you. So you can see, oh, I'm standing on the wrong side again, of course. Of course I am. at 13 centimeters, so you can see the big red blob that is Jupiter, right? This big red blob here. And yet, you see these wings, right? The wings that come off on either side. Well, that is where Io is, or Io, mainly. And you can see the two red spots on either side of the bigger one. That is the main portion of where the moon, you know, revolves around Jupiter. But if you notice, you can see also these kind of wings that come in vertical extent. Do you see that? See those both in 13 centimeters, and you can even see it better in 22 centimeters. Do you see how thick the wings are? That is all the dust from the volcanoes. And what's happening is those particles are literally bouncing. We call it bounce. The particles will bounce around the magnetic field that's attached to Jupiter, and it will bounce through Jupiter back and forth like this, all the way around the planet. So these rings, you're looking at a cross-section of these rings, but the particle ring that's creating radio emission is actually kind of like a sphere, a dome, all the way around Jupiter. Is that crazy? Along with this elongated, what we call the Io torus, because now you have all this dust that comes and spreads out, and the reason why it's spreading out, I think, is more gravitational than anything. It's being flung out, and so it's got this elongated kind of thing. But the magnetic side is why it's got these horns. But the horns are really a shell that go all the way around. This is one of the main reasons why Jupiter is so noisy, so incredibly noisy. It's got an insane amount of radio sources that it can use. So here's a plot from one of the papers. You can see here's Jupiter here, and you can actually see, so they've got one of the magnetic field lines. They've just, it looks like a dipole field line that they've locked around. So this is the Io, or Io. If I can pull my finger back here. There we go, down here. So that's the moon going around Jupiter, and you can see the equatorial orbit path. And as it moves around Jupiter, as it populates these different flux tubes, as it goes through as it's orbiting the Jupiter, as it goes through these different field lines magnetically, and I don't want to get too involved in the jargon here, but as it begins to move around, it populates different areas, and as it does that, the dust and everything else, it allows the cyclotron maser emission to occur. You've got these, what they're calling, I guess, the cone. What is it called? The emission cone, and that's following these field lines. Okay, see how this emission cone looks like a funnel? It's following these field lines. So as Io goes around its orbit, it's able to literally scream at every point around its orbit in radio frequencies, in different radio frequencies. And it's all a function, again, remember as we said before, the radio frequency noise is going to be a function of the density of the plasma. Well, at Io, or Io, there's a lot of plasma because all of that junk that it's spewing out is upping the density in those regions. So you're going to have higher radio emission wherever that plasma is denser. So you're kind of, in a sense, the radio noise is mapping out where all that volcanic dust and crapola has gone. And look at that. Oh, what a noisy, look at where all of that dust is, it's all over. It's actually a shell around the Jovian system. So the Jovian system is just riddled with radio noise, and radio noise at decently high frequencies because the plasma is so dense there, all thanks to Io and its volcanic spew. And the funny thing is that somebody asked me the other day, they said, do you think with Europa spewing water vapor into the atmosphere that we could maybe do a radio bounce off it, or we could get some type of emission off it? And I didn't think at the time. I said, well, it'd be hard, blah, blah, blah. And I talked about a couple other things, more having to do with trying to time these fountains coming off, these geysers coming off of Europa. I didn't even think at the time about this. Well, I don't even know if we could see it, even if we wanted to, in radio frequencies, because the Io emission is so great, from the Jovian system, that I would think it camouflage anything coming off of Europa. So I don't think radio frequencies are such a great frequency to sound anything other than the Io torus you know, if you want to know the truth. Now, I may be completely wrong, but I do know that that's the reason why the system is completely dominated by Io, and why frankly the Jovian system is so much louder than any other system, including the Saturnian system. And it's really all because of the volcanoes. You can thank the volcanoes on Io. Pretty cool, huh? Okay, let's see. So the only other thing on this plot I hadn't shown is they have several different types of bursts. They have the long bursts, the L bursts, and the S bursts, the short bursts. I don't pretend to know more about it than this, but you can see the long bursts are these you know, patchy duration, you know, reasonably short duration, I would say, but long relatively speaking to the other bursts, but patchy kind of broadband at this frequency range, and these are megahertz, or these megahertz or kilohertz, I can't tell. I forget. I can't see. It's too small for me to see. I'll see if I can look at it in a second. Hopefully you guys can see it better than me. But I think it's megahertz. So it looks like around 20 megahertz. So, you know, HF, getting into HF frequencies. But you can see they're kind of patchy. And then the short bursts are actually descending, but not descending very much, because you can see the scale range down here on the short bursts is really, really tight. But there are these microseconds bursts that are slightly descending, so kind of thing. That's what the sounds that they would probably make. Maybe not quite that long in frequency in terms of changing, but they are descending. Or wait, no, you know what? They're ascending. My fault. Time goes this way. So from low to high, right? That's how they go. So there are these very well-documented and well-known bursts in the Jovian system that are due to these types of emissions. And then, of course, when you look at the auroral foot points, this could give you an idea with the AKR emission. You look at the auroral foot points at the Jovian system. So you've got all this stuff going on already, just in the normal Jovian aurora, which happens all the time. It's not. They don't even need a solar storm to happen. A lot of it is actually happening. They're thinking it's happening, and thanks to Juno is actually finding this out. It's happening all the time, whether anything from the sun is hitting it or not. There's so many processes going on in the Jovian ionosphere that it's actually creating aurora terrestrially in that sense. So it's not just space weather, plus it's got all the complications of the space weather aspect from Io and everything else raining down on it all the time. There's always particle precipitation from Io as well as others. But you can see Io, Ganymede, Europa, you can see their foot points and how they drag all the stuff like little comet tails dragging in through the atmosphere. And all of that is not just light energy, that's also, they've got radio emission, kilometric radio emission from that too. So the Jovian system's a fascinating system to look at. You know, too bad, well, I don't know, I should say too bad that Earth isn't like that, but if it were, it'd be unlivable for humans. So maybe it's not so bad that we're not that interesting. But at any rate, for those of you who are worried about aliens coming and finding us because we've got our televisions on too loud, or Sirius XM radio is blasting, you know, David Bowie in space, don't worry about it. Jupiter's got you covered. Okay? So we're all fine. So, and with that, that is it. Oh my gosh, I can't believe it. We've made it, guys. We've made it. It's been 4 courses. It's been a long time, but we finally covered flare dynamics, with all of the precursor impulsive extended phases, the gradual versus impulsive flares, the effects of the radio emission at Earth, with all those all of the examples, and then we covered the solar flare myth with Hyder flares and stealth CMEs being the lowest end of Hyder flares, and now planetary radio emissions. So really, all that is left is lingering questions. You guys have any questions? Because this is it. We're buttoning it up when it comes to solar flares and radio bursts. And we're going to start moving on to solar radiation storms. That'll be the next thing that we talk about. So let me check to see if we've got some questions, okay? And I hope you guys enjoyed it thus far. Okay, let's see. Taurus field, okay, you guys, it sounds like you guys are having a good conversation. It's too late, aliens hacked our internet. Sounds like you guys have had good conversations amongst yourselves, which is great. I'm trying to see on Patreon if anyone has asked me questions. Nope, I'm good there. Watch your previous courses, and I must admit they're the best material online. Thank you. I can't pronounce your first name. Wojciech? Nowak? That's such a kind thing to say. I appreciate that. So give me excellent GM7 PBB. Thank you. I appreciate the thumbs up there on telling me the presentation's good. Great. I got on late, but will we watch? Yes. That's the great thing. I'm keeping these up for a while. I've had multiple requests, even though I told you for a while that I was going to take them all down and maybe re-edit them and package them, repackage them differently. But right now, I'm going to leave all the mini courses up on YouTube. So don't worry, I'm not going to take them down as of yet. And those of you who have the links, I may end up not making them public, but if you hang on to those links, I think you'll be able to continue watching them even when I make them unlisted. So if you're savvy, go in there and catch what those links are, because I don't think they're going to change. I'll always keep these online. Let's see. What do we have for questions? Thank you, Tamitha, very informative. Ask questions now if you have any. Are the radio bursts a way to shed energy? Radio bursts a way to shed energy, yes, absolutely. On the sun, that's part of what is all happening. They're generated by wave processes, all different types of wave processes. And honestly, it's really, everything is trying to come to some kind of equilibrium, whether it's a magnetic field coming to equilibrium or it's particles being in thermal emission, and you're trying to get things to what we call isotropize. You're always trying to make everything the same. Entropy is always trying to increase, and there's all sorts of different ways of making that happen. And radio emission is one of the ways that we shed some of that energy and help to isotropize things. Let's see. We are listening to you too, Tamitha, and convo between ourselves. We are learning. Oh, that's good. I love that. I love it when I come on and I'm looking for questions and I see you guys are answering each other's questions and debating. I think that's fantastic. That lets me know that this community is just, it's why it's one of my favorite communities, is because you guys are willing to teach each other and debate, amongst yourselves. And it shows me that yours is passionate about this stuff as I am, and that's so cool. Okay, Tamitha Scove, I read that electric solar wind sail is being researched. Oh, gosh. Oh, solar sails. Yeah, solar sails were big in the 80s and the 90s. We tried that then. I learned so much about them. They're dangerous, and I'll tell you why. Okay. Part of the reason why solar cells are problematic, especially in Earth's environment, solar cells are very thin. Solar cells are typically made out of things that are like mylar, very, very thin. Like the metal balloons, right? That's mylar. And the problem that we have with mylar and with materials that are super, super thin in space is that they're really, really susceptible to low energy plasma radiation. Everything in space is radioactive. That may come as a surprise, but it's true. Everything in space has got some charge, has got some energy, and when you have really, really, really thin materials, let me try a different way of explaining it. What you don't want in any material is to have a particle that's coming on it to hit that material and implant itself in the material and stop in the material. If you have a very energetic particle and a thin material, that particle will go right through the material and really not deposit what we call much energy. Okay, that energy is oftentimes called an ionization dose. If it's not displacing anything, it's an ionization dose, or you have ionizing and non-ionizing radiation. And when particles travel through materials, they deposit one of those two types of doses, which is a radiation dose, which degrades the material. The thinner the material is, the lower the energy the particle has to be to stop in the material. And that's the worst thing you want. When a particle stops in the material, it imparts all of its energy to that material. So it can do the most radiation damage if it stops in the material. The thinner the material is, the lower the energy required. The problem is, the lower the energy, the more plasma is out there. So in other words, if you look to the highest energy particles that are out there, you're going to find the fewest particles out there that have that super high energy. But for low energy stuff, there's a ton of particles out there. So if you have a really thin material, then you're dealing with the most dense of the plasma that can cause the most damage to your material. In other words, what happens, especially in environments like geo, for example, those materials will shred. I mean, they will darken, they will shred, they will disintegrate before too long. And it doesn't take long, a year, maybe, 6 months, maybe. We've had lots of that stuff happen, even with what we call entrance filters on spacecraft. There was one a long time ago, and I'm not going to talk too much about it. But we've had instruments that are trying to stare at the sun, and they've got to have these filters that keep out certain light frequencies out of the instrument. Well, these filters are super thin, and they launch them into these environments, and within 6 months the filters are breaking, and they're shredding, and they're degrading. Well, that's because of the radiation environment. So what we find is that the thinner the materials are, the more susceptible they are, and of course it depends upon the orbit. But that is a real no-no when it comes to solar sails. You have to have a thin material to have it be a solar sail, otherwise it won't give you much in terms of a solar sail. The problem is solar sails shred, and they disintegrate in space because of space weather. So how do you build a solar sail that's super thin and doesn't shred? Don't know yet. So solar sails are an idea that keep coming back. This isn't the first time. They've been around. They get killed when people who understand materials are brought in to be the subject matter experts. Then the idea dies, and then everybody forgets about it for a decade, and then it comes back up again because there's a new set of scientists with and engineers with new sets of ideas, and they say, hey, how about solar sails? So then they try it again, and the whole cycle repeats. So I've been through several of these cycles, and most likely the same thing's going to happen this time. It's a beautiful theory, but space is hard. And as a matter of fact, one of my space materials experts who I work with, and a very dear colleague of mine, Mike Mashiznik, he says, if space were easy, anybody'd do it. And it's not. And that's why a lot of these ideas come and go, because they just can't work in space. But we're slowly learning. So hopefully that answers that question. Okay. Let's see. So getting solar panels, the panels would degrade even faster from space weather. Oh yes. And there's a lot of heat when it comes to solar panels. Things that happen to solar panels is that they darken. This is what happens to glass, especially if it's got special coatings on it to try to keep it, try to increase its conductivity, or try to keep it from arcing or charging. Sometimes the coatings actually will darken, and now if they darken because of the radiation, now it's like putting sunglasses on your solar panels. Well, is that a smart idea? Don't you think the power is going to go down if suddenly you put sunglasses on your solar panels? Not a good idea. So we struggle with that as well. And yes, that happens a lot. And I can't go into more details about how, because some of that's proprietary. And it's the vendors, not me. It's not my it's not my information. But these are issues that in my day job, these are the things I have to deal with. And satellite design is not as easy as people think it is. We've just done a really good job of making it look like we can do everything perfectly the first time, but we don't, not at all. Okay, and it depends upon the orbit, because space is not space. Different orbits have different radiation involved, and there's different particles that are involved. And so something that could fly really well in a LEO orbit will do terribly in a GEO, but something that does, let's say something that would do okay in a GEO orbit, you fly it in LEO and it won't do well, because there's just these different things that take over in terms of being the hazard that you have to deal with. So how far can a solar flare travel? Well, conceivably, as far as light can travel. Solar flare, from that point of view, is light. It's light emission. It's X-ray emission all the way down to radio wave and beyond. So, it's like asking, how far can light travel? Well, I guess as far as anyone could detect it before it got scattered to a point where then it's just traveling somewhere else. It's just at a low level that nobody detects and can really identify where the source came from. So it's really that simple. What is your day job? Thanks in advance. I work for the Aerospace Corporation, which is a federally funded research and development center. It's basically a think tank. We basically are the technical arm of the Air Force, the American Air Force, to try to make sure they're not sold a bill of goods, because the Air Force in the United States, the Air Force is responsible for keeping all of the space assets safe, and that's where we come in, because we have the space expertise and the space weather expertise to know what's safe and what's not, and when they have anomalies or problems, we can pretty much suss out where the anomalies are, and what they were caused by, and how to get around them. And if we don't, then we go back to the drawing board and try to figure out what we can do better. But the issue, the main issue that we have to deal with for the Air Force and for other contractors, because we do this all the time, is to make sure that the contractors aren't being too cavalier about space. One of the things that people don't realize, for example, is that the Aerospace Corporation has had a huge hand in helping SpaceX. People think, oh, SpaceX is so smart, they know exactly what they're doing. Well, they do, because they've got subject matter experts who are looking over their very shoulder. And the reason for that, of course, is because we've got the Air Force who is actually using SpaceX. And they said, no, SpaceX, you will get our expertise and you will help, aerospace, come here, help us. So we have even big program offices that are stood up to simply for SpaceX. I mean, so anybody who thinks that some of these commercial entities are just doing it all on their own, not a chance. They lean heavily on what has come before. And every time they try to put up new things, they eventually, if they don't come to us right away, after a few failures, they do, because it costs too much. So they end up coming to us. So that's kind of what I do on my day job. What I tell people is that basically my job is to make all of the space infrastructure that you guys use on a daily basis and that I use on a daily basis, make all of that invisible to everyone else, so that you guys don't even know when there are problems. I mean, that's when we know we've done a good job, is that when people don't even know that there's space weather. The problem that has then caused for me, of course, is that now I'm trying to educate people about space weather, and I'm my own worst enemy, right? Because my job is to make sure that space weather doesn't cause problems, but then it means that nobody knows what space weather is, because space weather isn't causing problems. Yeah, well, we're beginning to fall behind that curve, because as new technologies come online, space weather is going to nip us in the butt, guaranteed. I shouldn't say butt, I should say bud, nip us in the bud. And I just don't want it to set us back with technology. That we have drones that are flying on GPS, and what if they crash into something or someone? Then what? They're going to ban all drones or slow the technology down so we can't use them? I don't really want that to happen either. I want us to do it right the first time as best we can. And so that's part of why I'm doing what I'm doing. So hopefully that answers that question. Let's see. Oh, you're welcome, Francina. Thank you for telling me that. I appreciate that. Should collaborate more with our Australians, Cicero and DSTG. It depends upon who you're talking about. I probably do. I collaborate with a lot of the scientists, and I have lots of conversations. As a matter of fact, next month I'm going to be going down, or next week I'm going down to the AGU meeting, and it'll be the first time I've been at AGU for 2 years, because they haven't been at San Francisco for 2 years. So I'll be going down there, and it'll be fun to be able to talk to a lot of the colleagues, international colleagues that I haven't seen in a couple years, and most likely some of these folks will be there. So thanks for that. I appreciate that. Gotta go. Thank you. Thanks, Pau. Thanks for being here. Let's see. Tamitha, I'm sorry, but I still don't understand how a thick solar sail doesn't absorb low energy particles too. A thick solar sail, it does. It does. The thick solar sail, but what makes it okay is if a thick solar sail is that if it's thicker, then it's only going to deposit stuff on the low energy stuff is going to deposit stuff up the top, and that top layer may slough off, but then you've got the other thicker layer down beneath. That's fine. A thick solar sail, however, can't be a solar sail. It doesn't work as well because it's got too much inertia. The whole point of having a solar sail that can be pushed by the solar wind or something else, or Lorentz force, is that it's so lightweight. There's so little mass that it can actually be buffeted along by the solar wind. Once you make it thick and heavy, and thick and massive with a lot of inertia, it's not going to be pushed. The force isn't going to be strong enough to move it. That's why solar sails have to be thin. You are correct. You are understanding. It's just that solar sails, by definition, have to be thin because of that. There's so little force being created by whether they're using it through the solar wind pushing it itself, or they're using it through what we call the Lorentz force, because of the magnetic and electric fields that are in the solar wind too. That you can actually use the Lorentz force to push these things magnetically. So hopefully that helps. Our low energy photons reflect, not photons, particles. The photons themselves aren't that big a deal. It's actually the particles, electrons and protons mainly. So we are actually talking radio, parts of atoms, right? Oh, I missed one. Okay. Olympic drones over every city now. They're very safe. And yeah, think Robocop. Yeah, but they're not very safe. They're not, and we're going to find that out very soon. And I don't know. I'm not going to go into the details of that in this particular course, but they're not as safe as people think they are. Thanks so much. We've consulted with aerospace. Yeah. So you guys know, what aerospace is about. For a long time, they didn't even like to have their name out there, because they were kind of a hush-hush organization, because they didn't want people tapping the subject matter experts. But as space has become a bigger place and a lot more players involved, Aerospace Corporation has actually become a much more visible entity. They are used a lot more heavily than they ever used to be. But yeah, they're considered a really good place to work. And really, if you want a lot of space expertise, that's a really good place to get it. Even NASA, people say, oh no, you go to NASA. Well, NASA actually gets a lot of their expertise from aerospace as well, especially when it comes to engineering. We are pinged by NASA all the time to help them with their technical solutions. So it's a very well-woven community. Let's see. If something bad was about to happen, would you tell anybody and cause mass panic, or just keep quiet since we'd be helpless anyway? I tell everybody. But I wouldn't tell everybody in the form of, oh my God! I wouldn't. I mean, what good does that do? I tell everybody, okay, we may be going offline for a little while, because there's a really large Carrington-class event that is headed straight for us, and this could be bad, folks. We don't know, because we don't know what direction the magnetic field is going to hit, because we can't predict that ahead of time. We did get a Carrington-class CME that actually clipped us just back in 2017. In 2012, we had another Carrington-class CME that didn't hit Earth, but it hit one of our satellites on the other side of the sun. Luckily, the magnetic field was flipped the other way, so that if it had hit Earth, it would have been a big storm, no doubt. But it wouldn't have been as big as let's say the Carrington event itself. It would have been as big as the 1989 event. As it was, it wouldn't have mattered. As it went over spacecraft, it doesn't care. The spacecraft could handle it, because it's not inside the Earth's magnetic shield. It's actually the Earth's magnetic shield that becomes the issue. Spacecraft are fine, typically, when a lot of these storms go by. The radiation storms are a bit harder for the spacecraft to take, but a big CME by itself, not a problem. But yeah, I would be giving a weather forecast that may not be. If you look at one of my most popular weather forecasts, this was one when region 2673. If you look on my YouTube channel, you'll see that. You'll see, I think it's the most popular video that I have. That one was actually featured on Russian state network, state-run television for a weather broadcast, because they picked up on the fact that this space weather forecast was important when it came to dealing with Hurricane Irma and Harvey. But I would give a forecast that's very similar to what you saw there. It'd be very matter of fact. It would talk about what we would do, because and I would make sure that I was live as I could be when that CME hit our upstream monitor, because remember, these solar storms, even when they hit us hard, it will take a little while to ramp up the effects. And so if we were to have big internet outages or big power outages or something, number one, down in Los Angeles, I'm probably pretty isolated. It has to be a really big storm to cause us problems down here. But I would be talking about it and coming online as soon as I knew, and trying to give everybody the most information as long as I could. But I do it as matter-of-factly as I could. I wouldn't be, you know, I'd be just like any other weather person who deals with, you know, the big superstorms that come. You try to be factual, but also, you know, give people the information they need so that they can make the right decision for themselves. And that's the best I can do. It's the best that anyone can ever ask of any type of weather person, terrestrial or not. Is the new Space Force going to have a Space Weather Center funding? I have no idea. Probably not. You know, oh my goodness, who knows? Our government is just, it's so crazy. Politics and the government is just so nuts right now. I try to stay away from it. I think if the Space Force actually happened and everything was taken away from the Air Force, there's good and bad with that, right? I mean, the Air Force has had it for so long. They've got a certain expertise that ramping up a new Space Force they wouldn't have. But then again, a Space Force would be only about space, so that would be their primary focus. Where the Air Force is really diluted. They've got so many other things that they've got to worry about, like the warfighter, for example. Here, it would be all about space and space assets, and space communications. So, you know, there's 6 on one hand, half a dozen on the other. I really don't know, and I don't have a crystal ball to be able to tell you one way or another. But I definitely won't be getting into the politics of it. Oh my gosh, ugh, yuck. Let's see. Okay, the space weather app from that other guy will give you an alert. Uh-oh, that other guy. Okay, that was funny. Let's see. Thank you for saying that. It's much appreciated. I hope that is that about the space weather broadcasting. Yeah, I would try to be as relevant as possible, but I'm not going to talk about buildings on fire. I mean, that's just silly. What I probably would spend a lot of time doing is dispelling the myths, you know, just kind of like what we've done a bit today when I talk about the solar flare myth. There are a lot of myths when it comes to solar storms, and I would be spending a ton of time saying, no, that's not going to happen, and answering a lot of questions. No, that's not going to happen. Don't worry, the building's not going to catch on fire. Don't worry, you know, your pacemaker isn't going to go out. You know, unless your pacemaker is the size of Lake Michigan, I don't think you have to worry about it. You know, there's so many things that are fear-mongering, and I probably would spend far more time trying to calm people down about all the misconceptions than talk up some of these scarier aspects. So hopefully that helps you. Hi, are you out of here? Okay, bye, babe. Let's see. Lol, Space Force could really just say USA is finally getting their own Pine Gap. Who knows? Who knows? Okay, Woodsy Mom, thank you. Yeah, so I thought so. Yeah, I thought you were asking about the space weather forecast. So yes, if you want something, if we do have a Carrington class event, or if we do have something catastrophic that's coming, yes, I will tell you the truth. I will say, oh my gosh, this could be. And I will say this is a serious one, folks. You know, but I would spend a ton of time trying to talk about as much of what it isn't as what it is. And I would be very honest about what we know a priori and what we don't. We don't know what direction the magnetic field is going to be when it hits, until it hits our upstream monitors. So we can see a massive solar storm that's launched, moving super fast, and all I can say definitively is, if it's moving at 3,000 kilometers a second and it's going to get here in 17 hours, low latitudes, look out, because you're going to get an EMP. Because when that thing hits Earth, it's going to make the Earth's magnetic shield go ooh, like this and crush in, and it's going to go fast. And so it's going to be what's called the E3 component of an EMP, which is the slowest end, the slowest end of an EMP. There's 3 types of EMPs that the grids are worried about, and there's E1, E2, E3. One is lightning, 2 is, I can't remember what they are. They're you know, nuclear detonation, blah, blah, blah. The E3 component is the geomagnetic storm component. That's when the Earth's shield is crushed inward. It's a very strong component, but it's slower acting. So the EMP is kind of a longer acting, but less intense. And so there are some ways to ride through that. A lot of ways are not. But it's the low latitudes that get hit with that, believe it or not. It's actually the very much lower latitudes. So high latitudes and mid latitudes, high latitudes don't suffer much. Mid latitudes suffer a little bit. The low latitudes are the ones that really suffer when it comes to EMP. And so, you know, I'd warn about that, because that's all I would know, would be that yes, we're going to get hit by something. and it will physically crush us, crush the shield a little bit, and then before the shield becomes the, because the shield is springy. So it will crush in and then go back out. And when it crushes in, it gets stronger. And then when it goes back out, it weakens. And so we know that we'll have an EMP. But after that, I don't know. This big solar storm may be a bumper car that crushes and then bounces off and rolls off because it's got the wrong magnetic field orientation. Or it crushes us and then sticks and stays like glue and pumps all its energy into our Earth shield because it's got the right magnetic configuration. And then we're in trouble. But I won't know that until it actually reaches our upstream monitors. And that's only not even if it's moving that fast, it won't even be half an hour worth of notice before we start feeling the effects. But it is a little bit of notice. So, hopefully satellite operators are paying attention. By the time we get one of those, let's say, I'm sure we will have some TV meteorologists who will be talking about it in public, on the nightly news. Otherwise, I've not done my job, and you guys can all pelt me with olives. Because if there's something as big as a Carrington-class event, and I don't have enough meteorologists following me on social media who have not already picked up on that, or I myself am not on the Weather Channel talking about it because no one's invited me to come on, I will be screaming bloody murder because it's, this kind of information needs to go out and people need to hear about it. They just need to hear about it in a sane fashion. And so we need to be able to talk about what is going to happen, and what we don't know could happen, and definitely what will not happen. And a lot of the stuff you see on YouTube about what these big storms do is not going to happen, because some of the stuff that they talk about is it's just fear-mongering craziness. So anyway, okay. Hopefully that clarified that. What's all the hoopla over the magnetic poles flipping? The Earth's magnetic poles flipping? The biggest hoopla there is about that right now is all our compasses aren't going to work very well. All of the maps are having to be redone, and all the field, we have even magnetic field maps that we use for satellites and GPS and everything else. All of that's having to be redone because the poles are migrating. It's the Earth's magnetic field is honestly it's a bunch of different types of magnetic fields all piled together. You have the dipole field, which is the main one, that's the strongest, and then you have a quadrupole field, and then you have an octopole field, and then you have higher order, what we call higher order terms. I won't go into the physics of why, but it's just the solution to a particular kind of problem. And everything is done by an approximation. And every single type of magnetic field that's added to this list, dipole, quadrupole, octopole, and so on, are weaker. Each one is successively weaker because they're lower order effects. The dipole is by far the largest. It has 2 poles, dipole, right? Quadrupole has 4 poles. Octopole has 8 poles. So the dipole field is what we see, and you have a north and a south pole, and this dipole is flipping. So for a short moment, during this flip, the dipole field will go to 0. Does that mean Earth's magnetic shield disappears? No, it means the quadrupole field is there. The quadrupole field isn't flipping. But it does mean that for a short period of time, we're going to have 4 poles that we're going to be able to see. Isn't that cool? Could you imagine? We got a northwest pole and a northeast pole and a southwest pole and could you imagine having all that? So then you have aurora at like mid-latitudes, and you got aurora in Hawaii and down in Singapore, and I mean, how cool for a little while. The problem that it's really going to cause is satellites. For satellites, not only are they going to have a weird magnetic field to deal with, but where are our radiation belts going to go? I mean, if you've seen, and I'll probably do a class on this at some point. If you look at what the magnetic field flipping looks like with some of the models that they've done for the magnetosphere, oh my gosh, it's like a tangled line of spaghetti. You look at all the magnetic field lines, and they're everywhere, and they're all weird, and they're all bent, and they're all kind of in this very strange, like taffy configuration. And so it's like, well, how can stable radiation belts even exist at that point? I don't know if they can. So our radiation belts may go away, which could make the environment better for spacecraft. It could make it worse. I don't really know. How well will it shield us from cosmic rays? I don't know. We may have different cloud formations than we do today. There's just all sorts of really cool things. But it doesn't mean the shield is going away. It just means that the dipole portion of it will go away for a short while, and then it will rebuild. and then we'll have to relearn space weather all over again. But it's really not that big a deal. And the reason why the poles are migrating so dramatically is because the dipole field component is disappearing, and the quadrupole field moments are taking over. As that moment takes over, its poles are in different locations. And so what was a north pole is now migrating to where the quadrupole field says the poles should be. And what you're probably going to see is the North Pole maybe bifurcates and becomes two poles. I mean, not in our lifetimes, but maybe in our great-great-great-grandchildren's lifetimes. You'll see the North Pole actually bifurcate into two poles. You'll see the Southern Pole bifurcate into two poles. And so we'll have the quadrupole field. And then that will last for a little while. And then the poles will migrate again and collapse back into a single pole for the north and single pole for the south, right, and move. And then we'll be back to a north-south pole kind of thing, but the poles will be reversed, right? What was north will be south, what was south will be north. Why it's a big deal, I don't really know. The sun does it every 11 years. The poles reverse. Haven't seen it affect the sun too much, right? Just gets kind of quiet for a little while, and then it gets really noisy, and then it gets quiet for a while. When it's really noisy, that's when the poles are actually reversing. So that's when we see what we call a multipolar sun, where the sun is just, it's got so many poles all over it. It's got coronal mass ejections and solar flares coming off of all sorts of weird angles. So really, there shouldn't be a big hoopla about it. It's just that because we're not used to it, we're scared of it, right? So hopefully that answers that question. Okay. Let's see. I'm glad there's that block that schizophrenic button on the chat. Oh no, is it getting weird? Okay, well, I'm getting some strange, some questions that are getting far afield. So I probably will slow this down and probably button it up here, guys. So if you have any last few questions for me, let me know. Robert Johns, I'll post on your page comment section later today on how our fires, in Washington had nothing to do with what you think. Oh, okay, you guys got some conversation going on. Oh boy. The solar reversal is late, isn't it? Well, the sun right now is not actually reversing. We're going into a new cycle here soon, and yes, this cycle isn't late, no, but the one prior to was. It had a very deep minimum. But actually during solar minimum, that's when the dipolar field of the sun is actually its strongest. That's when the sun is and that's why it's so quiet, is that the sun's field is really well ordered. And when it's well ordered, it doesn't need to shed a lot of energy. So really, it's when the dipolar field begins to flip. Right when it's flipping, that's when solar maximum is. That's when the sun becomes, is extremely active. It's shedding off energy left and right. But then when it becomes dipolar again, and the dipole field, grows again, it becomes very quiet, and that's solar minimum. So we're actually not at a reversal. The reversal will be at solar maximum, which will be in about 5-ish years, maybe a little bit more. So hopefully that answers that. What's the mental effect of cosmic rays? Oh gosh, here on the ground or in space? Cosmic rays here on the ground, not much. You get a muon every 2 seconds or so, plus neutrinos and a little bit of here and there. As you get higher into, around 40,000 feet or so, you actually can get a decent dose of radiation from cosmic rays. As you go into space, there's actually been studies about it. And if you look at some of my space weather news, I think a forecast I did for both tomorrow, and then I put it on my space weather news probably about maybe a month or so ago now, maybe a little bit longer. I talk about a medical study that was done on particle radiation, which is cosmic rays, that was done for an interplanetary trip to Mars. And there are psychological problems. There are lots of things. Anxiety is an issue. There are issues with long-term memory. There are issues with slowing down, functions and impaired cognitive ability. So they're seeing some of that, and I think they've done it in mice. Where these studies are going, I don't know, but they're finally doing test as you fly. They're finally trying to look at the low dose, long-term low dose element of radiation, which we do for parts all the time. It's a more realistic way of looking at how radiation is going to affect the brain. And yeah, go look at that. And like I said, I think I even have it in the title. where I'm talking about radiation dose, medical radiation dose. So check that out, and then you'll see the paper that we're talking about that goes into more detail. Let's see. Micronova. I'm not going to go into micronovas, guys. I mean, those are such low probability events, and it's all speculation. Talk to an astrophysicist about a micronova. I'm talking about space weather. I want to talk about events that actually have some relevance to our human lives now, and that we're most likely going to get hit by. Not the ones that will be once every 20,000 years, and maybe you'll be alive to see one. I don't have anything but speculative theories, and I don't think anyone else has anything but speculative theories about that as well. So, speculation is not something I'm into. Anyway. Let's see. Any others, guys? Otherwise, I'm going to shut this down. Okay? Tamitha, let's see. My group counted accidents and random crazy attacks is 30 to 40% more of them during sunstorms. Oh, okay, now hang on. Because if you're talking about cosmic rays, that's different. If you're talking about solar storms, geomagnetic storms, solar flares, things like that, solar radio bursts, there's a growing body of knowledge about the medical impacts of those. And geomagnetic storms, there's a lot of people who are geomagnetically susceptible. They are very sensitive to changes in magnetic fields and electric currents and things like that. Some of them, as a matter of fact, won't even, there's areas in the United States where people live because they're electromagnetically free. They're free zones. They won't even allow cell phones. People who have blood poisoning, for instance, mercury poisoning. I met a gal the other day, and she had horrible rash on her hand. And she says, yeah, every time I use my cell phone, see, look, she says, I get this rash. And she's scratching it. And I said, you don't have this rash anywhere else? She says, no, just on my hand. I said, is this your cell phone hand? Do you always hold the cell phone? She says, yeah. I said, do you have mercury poisoning? She goes, yeah, how'd you know? And I was like, well, because of the rash on your hand. People who have blood poisoning, heavy metal poisoning, oftentimes are more susceptible to electromagnetic disruptions, and they're just more geomagnetic. So they're susceptible to solar storms because that's the Earth's field wiggling. So they get general malaise or issues. People who have plates in their heads, they get itchy, or they get migraine headaches. They have hip replacements. Their hip replacement aches and burns. There's all sorts of things. People who have pulmonary problems have issues. People who have high anxieties have issues. I'm seeing all of these types of things repeatedly coming out in the literature and coming out from just people talking to me. And there really is something there. And the robust medical research that has to do with space weather is not up to snuff yet, probably because space weather is such a new field. But it's coming, and I'm helping. As a matter of fact, I have someone on my Patreon VIP committee who is helping me put together a database on these types of things. And so what we'll eventually do when we get it at a point where we can make it public, we'll have papers and things that seem to be as robust as we possibly can find, and see if they're credible, and then have them as information sources for people who seem to have medical issues or may be susceptible, so that you guys yourselves personally can go wade through this information and see if anything resonates, and maybe follow up on some leads and get yourself tested maybe for heavy metal poisoning, or some other things that might then help you define what it is, whether it really is a space weather susceptibility or it's something else. But as of now, gosh, it's such the wild, wild west when it comes to medical research relating to solar storms and even the solar cycle. That it's I don't have a lot of definitive answers for you yet, but be patient with us. It's coming. It's slowly coming. So, I have a son who is a bench jeweler, and I get concerned about heavy metals getting into his system, and he gets many headaches. Good info. Yeah, it's always good if you notice stuff like that, checking back to see if you've had any type of heavy metal poisoning through lead or mercury or cadmium. Sometimes we had these chromium in the water. There's all sorts of ways of getting heavy metal poisoning, and that stuff doesn't leave you, and it stays with you, and you become very susceptible to anything that puts out electromagnetic signals, right? So your Wi-Fi, in your house for your internet could be a problem, or obviously your cell phone, Bluetooth, right? All of that. They put out low-level signals, but they're still signals. And so those are some of your first hints. And then obviously geomagnetic susceptibility from solar storms as well. These things are real. I've seen far too many of them to say, oh, it's just, hogwash. No, we just don't know how to research them yet, and we don't know how to quantify it yet. But I think the science is coming. It's just going to take a while. So, okay. My pacemaker occasionally causes burning sensation. Haven't correlated with geomagnetic storms. Ron, where you need to be concerned, and I will say this realistically, where you need to be concerned is when you get on airline flights, especially right now. Pacemakers are not radiation hard, and they have soft resets when you fly because of cosmic rays. I have talked to ASIC computer brain manufacturers who have been contacted by medical companies who specifically are designing ASICs for pacemakers. And the people that have talked to me, I've seen them at ham radio conventions. They're like, when I talk to them about cosmic rays and soft resets and some of these pacemakers, they go, oh my gosh, that's why that medical company contacted me, because we make radiation hard computer brains and chips. And I said, oh, that's why they were contacting me. They're trying to make their pacemakers radiation hard. And the reason for that is there are a lot more people flying in airlines at high altitudes, high latitudes, over the poles, and they are absolutely finding that there are resets. I mean, can you imagine your pacemaker turning off and resetting because it just got hit by a cosmic ray, got hit by a proton, or got hit by an X-ray or something that caused a memory glitch and caused it to have to shut down and reset itself. So be very aware. You might want to research with your pacemaker, find out what the company was that made it, find out whether or not it's radiation hard, find out whether or not it's safe for you to fly if you have to fly a lot, especially if you're doing international travel, that type of thing, because it's no joke. These devices do reset. As far as solar storms are concerned, don't worry about it. Your pacemaker's real small. It's not going to be an induced current. See, this is one of those misconceptions. Everybody thinks pacemakers are going to get hurt by geomagnetic storms. No, they're not, but they will get hurt by space weather when you fly. So just be aware of that, Ron. It might be worth looking into if you have a pacemaker, okay? Anything else? You don't fly, thank goodness, okay. But if you know people who have pacemakers who do, please spread that information, because there's not enough people who know about that yet. And there's not enough medical research, although I could point you to some papers which are very robust. And there are some savvy medical companies that are trying to answer the call. But it's, technology just advances way too quickly. And so we don't get on top of some of these issues before they become an issue. They almost have to become an issue before people realize, oh gosh, maybe we should be smart about our airline companies are smart about the avionics in their airline, all the computers and stuff like that are in the avionics. Well, this is a computer in your chest. So we need to be smart about that stuff too. And as these types of cybernetic things, these types of devices become more medically implanted in us, we're going to have to become even more and more savvy about flying and the doses of space radiation and how susceptible these parts can be. So. Okay, let's see, guys. More funding and research has to go into solar weather, especially as we evolve into a Wi-Fi society. Agreed, and that's part of why I'm doing this. As I train TV meteorologists and we start getting it over the, if I can get TV meteorologists to be space weather savvy and they start reporting about space weather, and space weather becomes a second language in people's living rooms, then we have the whole world that will do our lobbying for us, right? Then we have the whole world that will be space weather savvy, and they'll demand more space weather research because they want to know why we can't tell the magnetic field of a solar storm right when it leaves the sun. Why do we have to wait till it gets here? Why can't we have something out there that can monitor it? And they'll be mad. It's like we can track the storms, the terrestrial storms, really, really well. We know their wind speed inside their vortex. We know everything that's going on with them. How come we can't do that with a solar storm? And so the public will clamor and get angry and lobby Congress for us. And and get the world's institutions to put more money into space weather, so that space weather will eventually be on par with terrestrial weather, which is where it should be. And it's going to need to come sooner than later. So that's yet another motivation for me doing what I do. So again, I appreciate everything you guys do to help me help the world, right? Because we're all in this together. So I fly a lot, and this is interesting, but something I've considered: artificial joints impacted. I don't know. I would think for flying, I think computer parts are a bigger issue. Artificial joints will be an issue, for geomagnetic storms, if they're metal. If they're PMMA, things like that, acrylite, I don't think so. Anything that can conduct electricity, though, is an issue. But it won't be an issue up in an airline, really, because what's inducing the currents in your body is not the Earth's magnetic shield so much, but the currents that are induced in the ground that you're walking on during a geomagnetic storm. Then those currents will induce stuff inside your own body. So it's really not, if you're flying in the air, you're not touching the ground, so it's not going to be a big deal. But computer parts, anything that has a brain in it, could be affected as you fly because of cosmic rays, and because of solar radiation storms when they happen. Once we start getting active again and we start getting solar radiation storms. I wrote to a TV station if they were interested in space weather. They said no until the public wants it. Right, exactly, and very soon it will happen. Let's see, I was seeing something that Jerry wrote. Thanks, Jerry, for answering that. That's so awesome. Thank you so much. One of my VIPs, Jerry Ryan. Hi, Jerry. Thank you so much for answering the question there. I appreciate that. These guys, my VIPs, help me very much to field some of the questions that I can't get to, and my hat's off to them for helping me so much. Yes, until the public wants it, right, and that's exactly what we have to do, is we have to educate the public. How can the public want something that they don't know exists, right? All they know is that my GPS went out today, or my Sirius radio, XM radio got screwed up, or, I can't, I don't feel good today. They don't necessarily understand what really is happening, or, I'm stuck in Copenhagen because, they shut the airport down. I have no idea why, and we're stuck here for 4 hours. What, kind of thing. Or I'm a pregnant woman and I'm dosing my baby with more radiation than my baby's supposed to have, and yet I have no idea that's happening to me because I'm flying during an S3 radiation storm and nobody told me. These are things that I want to be able to have people know, and once they know what's going on, then they feel empowered by it. And they make space weather their own, and then they ask more questions, and then they want to know more. I mean, it's exactly the way things happened to me on social media when I first started doing this, space weather broadcasting, is that I got a few questions, I answered them, and then that brought me more questions and more people with more questions. And then it just began to build from there, and it's kind of really grown quite quickly. Even over solar minimum, I figured people would be saying, I don't care about space weather anymore. But over the past 2 years, I've grown probably larger in the past 2 years than I've grown during solar minimum than I've grown the entire time prior to that during, that was higher, when the sun was more active. So we'll see what happens when the sun really kicks off again, if we really start growing at that point. But I think this community is getting bigger, it's getting smarter, and it's branching out and even educating more people. And I just want that wonderful process to continue, because all together we are going to make the world space weather savvy. And we're gonna make sure that by the time your sons and daughters are going to work on the asteroid, mining it for their day job, that they're going to be safe up there, and they'll know, go into the underground bunker because the S3 radiation storm's coming, or get the hell off that rock and come home, because you don't want to be up there when that storm hits. Those types of things, and that's going to become even more important as time goes on. So. My wife has allergic reactions on the 11-year cycle. Interesting, George. See, you'd be someone who would benefit from some of these papers that we're putting the database together on. So yeah, pay attention to that. On one of our local news channels in Minneapolis, the weatherman does mention space weather from time to time, and I'm glued to the TV when they do. Thank you for letting me know that. That is fantastic. Yeah, in Minneapolis, because you can get space weather, you can get aurora, right? But there are other things too. Emergency radio is a problem there. GPS would be a problem there. You cannot do GPS safely under aurora, because your drone will fly very erratically, because it's losing lock on the satellites and gaining a lock on other satellites that then give it a totally different solution, because everything is so wavy up there with the aurora. I've actually seen telemetry from a drone that was struggling, and it was carving this banana in the sky that was like 50 feet wide by 30 feet high in the sky, and it was all because it couldn't get a decent lock on any of the satellites, and it was under aurora. Imagine your Amazon Air drone trying to deliver a package while it's doing that in your backyard. I don't think so, but this kind of thing is what's coming. Just think 100 years from now, Tamitha will be the space weather pioneer. Oh, that's cute. 100 years from now, I'm going to be dead. So I'll be in the ground. Yeah, you know, I would love that. I would love if this legacy could live beyond me. You know, that's a big goal of mine. So that you know, we bring us in. Someone very famous said you know, for when it became the 21st century, he said, you know, for the 21st century, it seemed like it should be really cool, but it's really boring thus far. There's nothing really that makes it feel like the 21st century. And I'm hoping that before I die, I can change that and make us feel like, you know, when we come home and we turn on the news and we see space weather reports and it's about our sun and what the near-Earth environment is going to be like, you know, it'll feel like the 21st century finally. So I'm hoping to do that before the 22nd century, let's put it that way. So thank you for that. I appreciate that. Okay. Last year, 4 of our guests lost their drones while flying at twilight. Yes, yes, nightlight films, yes, absolutely. The dawn and dusk are the worst times to fly, even during quiescent space weather. That is probably the kind of space weather that you can count on. Dawn and dusk are probably, for filming, is one of the best times to fly, but you have to use VFR. Be very careful when flying GPS-enabled drones during dawn or dusk, even the few hours before or after it. Because even though the sun either may already be up or not up, depending on which side of that line you're sitting on, the problem is that the upper atmosphere is still changing, because the upper atmosphere sees the sun differently. In other words, the higher you are in altitude, the longer you can see the sun, the longer the sun stays visible over the horizon. So the gray line, as we call it in amateur radio speak, that dawn-dusk line isn't a line, it's a region. And it goes from higher altitudes down to lower altitudes, and it creates a gradient, you know, a gradation of what we call conductivity, because the sun, the light from the sun creates more it increases the conductivity, it creates more electrons. It ionizes these particles. Sorry if I'm getting too much jargon. But it creates a difference. So there's a difference and a change that's occurring in the different at the different heights in the altitude or in the atmosphere. And that change itself is what makes signals going through it get really screwed up. So GPS signals during dawn and dusk and even a few hours before and after can be really messed up very easily. So yes, it's a very dangerous time to fly. And then of course, if you have a solar storm on top of that, it just exacerbates that. So yes, be very, very aware. And thank you for letting me know that you've had guests that have lost their drones while flying at twilight. Thank you for letting me know that. That's another anecdotal example that resonates with me very much and lets me know that I'm saying the right things when I say stay away from the dawn-dusk terminators. I say that a lot when I'm talking about GPS, and that's exactly what I mean for that exact reason. Oh, it's Adrian. Hi, Adrian. I didn't realize nightlight film. That's right. That is you, isn't it? I completely spaced. You never told me that, though. You've talked to me before. We never talked about people losing their drones. So thank you for letting me know that. And of course, you know, you already know you got to be very careful around your aurora. But that's something I would love to get more data on, is how badly are you scintillating under the aurora, and how more exacerbated is it by going, you know, by it being twilight as opposed to being pitch black. I'd definitely like to talk with you more about that, because that's really important to me. Okay, gotta go. I feed the horses. Thanks again. Thanks, Espens. Yeah, I'm ready to go too. I'm tired. You can hear my voice is kind of cratering on me. So, The Terminator is a tool we use for working really long distances. Yes, right, the gray line. Oftentimes you can get, that's when you get northern hemisphere to southern hemisphere, cross-hemispheric propagation, because it makes really good waveguides. Absolutely, it can be an absolutely magic for amateur radio. So thank you for mentioning that, Ron. Do I ever watch Suspicious Observers on YouTube? Oh, I'm not going to get into that. I know Ben Davidson's stuff very well, and he's someone I love. I love him and I hate him at the same time. I love him because he's a great space weather advocate. I hate him because not only is he a fearmonger, but he also asks people to not trust scientists. He makes a pretty penny off of scientist data and scientist missions and all of the stuff that we do, that we put our blood, sweat, and tears into. And then he tells people don't trust us. And it's like, Ben, you're making money off our data. You're making money off of my community and the people I care about. And you're biting the hand that feeds you. Please stop. Just don't do that anymore. If you want the data and you want the missions to continue, stop telling people to hate scientists, because the missions that then you rely on to do your space weather broadcasts, those missions are going to go away. And it's going to be thanks to people like you who are telling everybody else don't like us and don't trust us because we're bad people and that we're keeping data from you. No, we're not. It's just that space is hard, right? And when we get bad data and NASA makes us put out that data, whether it's good or bad, whether it's operational or not, and the data is terrible, and big chunks of data are missing, it's not because we're hiding big events and aliens. It's because there's a filter wheel in the way, or the spacecraft has an anomaly, or you're looking at a 30-year-old spacecraft that's being held together with baling wire and bubble gum, and it's like Soho. And it's got so many problems, it's surprising that it's even functioning anymore. We are so hamstrung in space weather when it comes to funding that we are making spacecraft that had a 5 to 10 year lifespan live for 30 plus years. I mean, family pets don't live that long, and yet we're making our spacecraft live that long. And they're only living that long because the scientists are so smart, and the scientists are so careful, and they love these things like they're babies, that they will find any way that they can to engineer a way to keep these things alive, even when they really shouldn't be alive anymore. They're on life support, a lot of these spacecraft are. And so when we hit people like Ben, who are making money off the data that these spacecraft the data these spacecraft are providing, and yet he's bagging on the team that's keeping that spacecraft alive, that is a personal affront to me. And so that's why I love to hate him. I love him for being a space weather advocate, but I hate the fact that he is ripping on the very people that have made him rich. Okay, so there it is in a nutshell. Okay, astrosociology, the love-hate relationship, absolutely. It is, it's absolutely, and I love it when he's not part of that astrosociology misrepresentation, and I hate it when he is. And he does both, he plays both sides of the fence. And so it's, it's one of those, kind of thing. So I will always be torn when it comes to Ben, and that's probably the way it's always going to be. I'm not asking him to change who he is, except to be more fair, especially when it comes to realizing that he's gotten rich off the backs of scientists that he then spits on. And that is not okay. Morally or ethically, it's not okay. So, anyway, guys, Ken Wheeler's magnetic theory regarding are interesting. Have you seen him yet? No, I don't think I know Ken's stuff. If it's the electrocosmology stuff, I'm not all that. I'm not all that interested. A lot of stuff there is it's too fringe for me. There are a lot of questions that are speculation because it's based on systems of systems, and a lot of times we aren't that far in understanding the fundamentals of the physical processes involved to be able to answer some of these bigger questions of the systems connected to this system, connected to that system. So it doesn't do me any good to go there because it's just too far afield. I kind of hover right at mainstream science, and then I dabble in the areas that are the fringe fields because they help push the mainstream field forward. But then again, you need the mainstream to rein in the fringe fields and give the fringe fields the data that is robust enough that they then can go speculate. So I leave the speculation mainly to them, and I stick mainly with my space weather community. Plus, that's what everybody here pretty much wants. There are not a lot of academics in this group. A lot of these people rely on space weather every day, so I try to keep it more to the operational stuff, because that's, and what impacts people on a daily basis. And I've got to keep my focus on that. So that's really what I do. Okay, guys. Yes, I need some tea. Thank you, Ron. My voice is, I'm losing it. So I appreciate that you don't mind looking, but remain skeptical. Yeah. Okay. I don't know if that was for me. All right, guys. Thank you for your candor and your honesty. You're welcome, Karen. I will always try to. I'm definitely not omniscient. I won't even begin to say that. And when it comes to things like astrophysics, cosmology, some of these other areas, I will flat out say, go ask an astrophysicist. Go ask an astronomer. I don't know. There's a lot of areas of space that I don't know anything about, and I have no problem telling you what I don't know, because it's just too much to know. And that's one thing you can always rely on with me, is that I will be the first to tell you if I don't have the answer. And I will definitely tell you, if I am speculating, I will tell you it's speculation. And then I'll probably only take it so far, because in the end, I just kind of have to shrug my shoulders and go, I don't know. So, okay, guys. Thanks. Oh, Daniel, thank you. Okay, it was. Appreciate it. All right, guys, I think that's it. My voice is pretty much gone. I hope you enjoyed today's course. And I believe if my Patreon crew is going to want to have me move on to solar radiation storms, then that is going to be what the next course will be, probably sometime in January, okay? So until then, have fun, and there's lots of other courses for you to review if you want to take a look back. And that's pretty much it. So thanks again, guys. I'll talk to you all soon. It's been a great conversation today, and I appreciate it very much.